today I am going to present about my work, that is about optimization and efficiency improvement of lead-free perovskite solar cells with CuSBS2 as HTL. So in this, I used a numerical study and modeling of this device by using SCAPS 1D software. So these are the contents I am going to explain: motivation, introduction, about work done, and results, references, and the conclusion. So first, motivation for choosing this solar cell topic is, if you observe, the electrical energy demand increases day by day with the increase of industrialization and civilization, and most of these needs are fulfilled by the burning of fossil fuels. But fossil fuel burning causes serious serious threat to environment. So the demand for clean and renewable energy sources increases progressively. So for that purpose, we are choosing this renewable energy. Under this renewable energy, solar energy is one of the examples. This solar energy is most sustainable, clean, eco-friendly, which meets the solar world's energy demand. So first, what is meant by a solar cell means a solar cell is a photovoltaic cell which converts the sunlight into electricity. So a solar cell is made up of semiconductor materials, which consists of a P-type material and N-type material. So coming to the one working principle of solar cell, so it consists of P-type layer and N-type layer. In P-type, holes are the majority charged carriers, and in N-type, electrons are the majority charged carriers. So near the junction of the two layers, the electrons on one side of the junction move into the holes on the other side of the junction. This creates an area around the junction. This is called the depletion zone. When sunlight strikes on the solar cell, the electrons in the absorber layer ejected, which results in the formation of holes which behind the escaping electrons. So if this happens in the electric field, the field will move electrons into the N-type layer and holes will move into the P-type layer. So in this way, the solar cell works and it converts the sunlight into electricity. The main performance parameters used to measure the performance of the solar cell are open circuit voltage, short circuit current, fill factor, and the conversion efficiency, or we can call this one also as the power conversion efficiency, PCE. So these are the different types of generations of solar cells. Basically 4 generations of solar cells: first, second, third, and fourth generation solar cells. So in the first generation solar cells, we are using the crystalline silicon. So in that we have monocrystalline and polycrystalline. Crystalline silicons are up to now, it achieved up to 25%, but these are expensive to manufacture. So because of that, we are moving to second generation, that is thin film solar cells. So in that we are using amorphous silicon, CIGS, and CDTE thin film solar cells. So these are takes much more time to fabricate. And next, third generation solar cells is and efficiency is also less in thin film solar cells. So next, third generation are the perovskite solar cell, dye-sensitized, and multi-junction solar cells. So here I'm mainly concentrating on the perovskite solar cells. So here these solar cells are made by using the perovskite material. So these are having the high efficiencies, and cost is also less compared to the first generation and second generation solar cells. And next, fourth generation solar cells are the hybrid solar cell. That means combination of these solar cells comes under the hybrid solar cell. These are the different generations of solar cell. Coming to the perovskite solar cell, a solar cell which uses perovskite material is known as a perovskite solar cell. What is meant by a perovskite means, a perovskite is a material which is having the crystal structure of AbX3, where A and B are the cations and X is the anion. This is the perovskite crystal structure. Generally, we are using this perovskite material in the absorber layer. The total photoelectric conversion takes place in the absorber layer. So if you see the structure of the perovskite solar cell, these are the layers. So we have transparent conductive oxide TCO layer. In that we are using fluorine doped tin oxide, FTO, ITO, ZNO, like that. And after that we have electron transport layer, ETL. This layer is used to allow the electrons and it blocks the holes. It allows electrons to the perovskite absorber layer, that is PAL. This is the heart of the solar cell. Total photovoltaic conversion process, that is conversion of light from electric to sunlight to electric conversion takes place in the photo absorber layer. So after that we have hole transport layer. This layer allows holes and it blocks the electrons. So finally we have back contacts or electron. This is the structure of the perovskite solar cell. So the features of the perovskite materials are, these are having the tunable band gap, and these are having the long charge carrier diffusion lengths and high absorption coefficients, and it has strong absorption coefficient. These are the main features of perovskite materials. So this is the work done here. I modeled this device by using SCAPS 1D software. It is a solar cell capacitance simulator, which is a one-dimensional software developed by University of Zen. So this is the configuration I used. So here FTO is the transparent conductive oxide, TiO to titanium oxide is the electron transport layer. This methyl ammonium, so tin iodide is the absorber layer. Copper antimony sulfide, here it is the whole transport layer. So back contacts, here I studied different types of back contacts, but I choose a nickel as the best back contact for this structure. This is the structure of the solar cell I have implemented. So why mainly lead-free perovskite solar cells are needed? So even though we are getting high efficiency with lead-based solar cell, but lead is toxic. So for that it causes serious pollution to environment also, which is non-toxic. Here if you consider lead-free, which is non-toxic, so that's why I use a lead-free perovskite, that is methyl ammonium tin iodide. So here CuSPS2 is the whole transport layer. Here I use different HTLs also. I studied with Spiro, OMTD, Cu2, OPTA. Out of all these, copper antimony sulfide is the best HTL. Why? Because it has high absorption coefficient and it has good stability compared to remaining all whole transport layer. That's why I chosen copper antimony sulfide as the whole transport layer here. So from my structure, these are the performance parameters I obtained: VOC, JSC, fill factor, and power conversion efficiency. So after optimizing the structure, I got this 29.74 efficiency. So these are the parameters I studied in this simulation. So different thicknesses I have varied for absorber layer thickness from 0.1 micrometer to 1.5 micrometer, and HTL thickness also I have varied from different ranges. And each layer I have added some defects, and at the interfaces I added some defect density of states, series resistance, shunt resistance, temperature, and I use different back contacts. I have studied the effects of all these parameters in this work. So these are the parameters I used in this simulation. For different layers, I used the thickness, band gap. So these are the parameters I used in the simulation. So these are the results. So first one shows the JV characteristics curve, which is current voltage characteristics curve for the optimized thickness for the optimized structure. So for the optimized structure here, the thickness is 0.7 micrometer for the absorber layer and 50 nanometer for the HTL. So from the optimized structure, I obtained these parameters, and this one is the quantum efficiency curve. This quantum efficiency is the ratio of number of electrons captured to the number of incident photons. So from this graph, if you see, the quantum efficiency increases from 300 up to 700 nanometers. After that, it starts decreasing. That means the amount of light conversion takes place in the visible region. So this is about the JV characteristics and quantum efficiency curve. So this is the effect of absorber layer thickness on the performance parameters of the solar cell. So I varied the thickness of the absorber layer from 0.1 to 1.4 micrometers. So these are the variations in VOC, JSC, FF, and PCE. So from this graph, we can say that VOC is decreasing and JSC is increasing, and PCE increases and FF decreases. So after that, these are the different whole transport layers and thickness of each layer. I have varied from 20 to 100 nanometers like that for CuSBS2, Cu2O, Spiro, and PTAA. So these are the parameters varied for different hole transport layers for different thickness. And effect of temperature also I studied. So as the temperature increases, the PCE decreases. So these are the different parameters I have studied with respect to temperature. And density of states. So valency band defect density effect on fill factor VOC, and these are the effects I studied. And these are the interfacial defects. So interfacial defects have strong influence on the power conversion efficiency. These are the interfacial defects I have studied. So I have studied two types of interfacial defects. One is at the absorber and HTL interface, and other one is at the ETL and the absorber interface. These are the performance parameters variance with respect to interfacial defects at the ETL absorber interface and absorber HTL interface. And this is the effect of series resistance and shunt resistance on the performance parameters of the solar cell. So what is the effect of series resistance and shunt effect? VOC and JSC, if you see series resistance effect, almost it is constant, and FF and PCE decreases. So this is the effect of shunt resistance on open circuit voltage and short circuit current. And these are the different back contacts are used. So nickel, platinum, copper, gold are used different back contacts. So each back contact metal for work function is different. Based on the work function of the metal contact, the efficiency varies. So these are the different efficiencies I achieved with different metal contacts. So out of all these, I achieved high with nickel and platinum. Platinum, I achieved high efficiency, but compared to nickel and platinum, nickel gives the high, nickel is more better than platinum. That's why I chosen nickel. Nickel as the best back contact for perovskite solar cells. So these are the result I obtained with the different metal contacts. So finally coming to the conclusion. So here I used the SCAPS 1D tool for this structure. So I have studied all these different parameters: thickness, defect density, density of states, interface defect density at two interfaces, series and shunt resistance, and temperature, and various back contacts. These are the obtained optimized parameters. So based on these results, we can show that these lead-free perovskite solar cells are the potential candidates for the nowadays technology. So these are the references I used. Thank you, sir.
Thank you, Jyoti. Any questions? Okay, thank you. You can continue with the next talk: efficiency improvement of CUSB S2 experimental thin film solar cells by numerical model.
Okay, sir. So this is the another work I done related to thin film solar cells. So in this work, mainly I have taken one experimental work, and I have completed the experimental, compared the experimental results with the simulator results, and after that I have optimized certain parameters. So in this, compared to experimental results, I improved the efficiency. So that is the efficiency improvement of copper antimony sulfide thin film solar cell. Here I have done the simulation related to thin film solar cell. So same contents. So this is my motivation, and again solar cell. So coming to the thin film solar cells comes under the second generation solar cells. So these thin film solar cells uses the thin films in the device, so which uses thin film materials, and In that thin film, mainly we are going to use amorphous silicon CDS and CIGS solar cells. So this thin film solar cell is cheaper but less efficient than the crystalline silicon solar cells. And so coming to my work, so this is the structure I used. So here, if you see, this is the back contact I used. AU gold, Spiro OMETED is the whole transport layer I used. This copper antimony sulfide here, it is the absorber layer like that, and IN2ST and CDS, these are the N-type buffer layers I used. So because of using these N-type buffer layers, there is an improvement in the efficiency. So I simulated this structure with adding IN2ST buffer layer and without having IN2ST, IN2S3 buffer layer. What I observed from this is, by adding a window of 2 buffer layers, there is an efficiency improvement with this IN2ST. And SNO2F, this is the transparent conductive oxide, which is fluorine doped tin oxide. I used, this is the structure of the thin film solar cell I simulated. Here also I used solar cell capacitance simulator tool. So this is the structure. These are the obtained parameters. So from the experimental results, these are the 1.72 efficiency they got. But for the same, I simulated, I got 1.86 efficiency with VOC, JSC. And so in this, I studied different parameters, that is thickness, defect density, interface defect density, series resistance, and shunt resistance. So these are the parameters I used in the simulation. So for each layer, I used these parameters in the simulation. So these are the JV characteristics curve from the experimental results and the simulator results. So this is the current voltage characteristics from the experimental results. These are the simulated curve. And this is the effect of CUSB S2 thickness on the FF and PCE. So mainly here in the experimental work, they have considered 0.18 micrometer thickness for the fabrication of the device. So for the same thickness, I achieved here 12% efficiency. So how I achieved this efficiency compared to experimental result means, so if we increase the at the interfaces, if we increase the interface defect density, the PCE is going to decrease. So if we vary the interface defect density from some 10 to 10 power 20 per cubic centimeter like that, the efficiency varies based on the interface defect density. And by considering the effect of series and shunt resistance, I have improved the efficiency from that 1.7 to 12%. These are the different performance parameters with respect to thickness of this CUSB S2. So here I have varied the CUSB S2 thickness from 0.1 to 1 micrometer. So if you see the thickness with respect to VOC, JSC increases, and FF and PCE also increases by increasing the thickness of CUSB S2 from 0.1 micrometer to 1 micrometer. So these are the JV characteristics and quantum efficiency curves for the simulated results. So for different thicknesses, these are the JV curves for 0.1 micrometer, 0.2 like that for 1 micrometer. These are the quantum efficiency curve. So here also photovoltaic light conversion takes place near to the visible region. So from the quantum efficiency curve, we can say that the photovoltaic light conversion takes place near the visible region. So here, mainly I achieved the efficiency by varying the different parameters, 12.6% efficiency. So in the experimental results, I added. So why? Because at the time of fabricating the device, we automatically add some amount of defects. So based on that, in the simulation also, I added some defects in each and every layer, and at the interface also, I added some defects. So based on the variations in the defect densities and the effect of series and shunt resistance and the effect of some doping concentration. So based on all these parameters variation, I got this 12% efficiency. So mainly these results are obtained by varying the interfacial defect density at the interface and the defect density at each layer, and by varying the series resistance and doping. So from this work, I can conclude that compared to experimental results in this simulated work, I can improve the efficiency. Okay, thank you, sir.
Presentation is multi-object. Am I audible, na?
Yes, you are.
Okay. Multi-objective binary cat swarm optimization for optimal design of CMOS ring oscillator. Myself, Vishnu Prasad De from KIT University, Bhubaneswar. So what is the challenge of analog or RF circuit design? That is the performance parameters are large and difficulty arise with the complexity in the growth of VLSI circuit and complex trade-off problem between nonlinear objectives and as well as the effect of short channel. Optimal design solution, evolutionary computation is a competent technique to design analog and RF circuits. Goal is here, optimization process will be automated with a high level of accuracy. So different algorithms will used for different analog VLSI circuit. Among these PSO, particle swarm optimization, genetic algorithm, artificial bee colony, that algorithm are famous. And in this context, we are discussing about the multi-objective binary cat swarm optimization for the optimal design of ring oscillator. That is a 9-stage ring oscillator circuit. So our objective is to application of this multi-objective binary cat swarm optimization for optimal design of CMOS ring oscillator circuit. Actually, in this algorithm, we develop for the behavior of cat. Most of the time, cat is in rest position, and when it finds some target, it will basically run after this. That is called the tracing mode and seeking mode. So in multi-objective binary cat swarm optimization, the behavior of cats are modeled algorithmically. Now here we have discuss about that is the there is a 9-stage ring oscillator circuit, and that is the application is clock signal generation, and we consider the design parameter as oscillation frequency, phase noise, power dissipation, and figure of merit (FOM). The design procedure summary: we have considered the oscillation frequency, F oscillation, and the total capacitance, the average power, the phase noise, and the figure of merit. That thing, and my design problem is the design problem can be represented as follows. That is the minimization of phase noise, minimization of power dissipation, and minimization of figure of merit. We consider the ring oscillator will oscillate with the frequency of 2 GHz. So that is the ring oscillator circuit consists of the CMOS inverter. So there will be NMOS and PMOS. So we taken width of the NMOS and width of the PMOS in a certain range, and we fixed for L for both NMOS and PMOS, and a particular sets of data will find out from this algorithm. That is the length of the channel, that is the width of the NMOS and width of the PMOS you consider in this range, that is in the nanometer range, and the optimal value achieved from this algorithm is that one. That is written in that side. Now these dimensions are now again implemented in Cadence so that we get the performance parameter. So here we use 90 nanometer technology. The frequency is of 2 GHz targeted, and we achieve 2.005 GHz. And optimal power dissipation at the circuit level is 78.5, and phase noise is -86 dBc per hertz. And along with the equation, we use to calculate the figure of merit, that is of -149.06. That is the transient response for the ring oscillator circuit. That is the phase noise plot of the ring oscillator circuit, and that's the DC power dissipation. That is called average power dissipation for the ring oscillator circuit. So in this work, the multi-objective binary cat swarm optimization used to achieve the design parameter for the ring oscillator circuit. And these optimal design parameters are used to implement the ring oscillator circuit in Cadence software. And we achieve the oscillation frequency of 2.005 gigahertz, a per DC PSN of 78.5 microwatt, and phase noise of -86 dBc per hertz at 1 megahertz offset frequency. And that are the references. Thank you.
Okay. Yeah, so thank you, Vishnu. It's a nice presentation and nice work. So just few small queries now. So the first question is why you have chosen the number of ring oscillators to be 9?
Ring oscillator is hello.
Why not say 5, 4, 3 or 10, 12, 13?
So actually, you have to fix for the oscillation frequency of 2 gigahertz.
Yes.
So it is basically 1 by twice n into 2p TP. So depending upon the value of n, the number of stage, we can set a particular frequency. Okay, if the number of n is less, so frequency will be high. In this case, depending upon the average propagation delay. So for setting this oscillation frequency of 2 gigahertz, we are checking that if we consider the number of stages is equal to 9, it is validating that thing.
Okay, thank you. That answers one more question. During this oscillator design, you have varied this length and width.
Yes, in this case, actually the algorithm.
So what is the current technology? Are you aware?
We use 19
So
nanometer.
why not fix that and start with other things?
Actually,
Because
we
the
use
lowest
19
of the W by L ratio, which I think have a best performance.
I cannot hear you properly.
Okay, sorry. There is a little bit glitch we are facing, technical glitch. Let me try something else.
Yeah. So is it audible now?
Yeah, this one.
Okay. Thank you. So the question is very simple. That why is you are this W by W ratio also you are changing? Because W by L is a parameter which comes from the fabrication aspect. Okay, so the technology, fabrication technology already you might be choosing one and then studying that fixed. So why your W and L are still varying? It is not a simulation aspects anymore. Whatever comes from the industry standards, you will be using that.
Actually, what you want to do?
Or else you are varying this W and L for your NMOS and PMOS. So
Actually,
NMOS, PMOS thickness width are different, you are saying.
I have taken a range. Within this range, what is the optimal solution that is achieved from this particular algorithm? We set it. We get this result from this algorithm. Then actually we feed it to Cadence with this particular dimensions. Next step we can actually include the capacitive effect, because after layout we have to add the capacitive effect. So after using capacitive effect.
Okay, I got the answer. Thank you.
So now I'm going to tell about a metasurface-based bandwidth enhancement of miniaturized dielectric resonator antenna design for wireless communications. So here we are designing a DRA. So coming to DRA, dielectric resonator antenna, is designed to overcome the problem of microstrip antenna. DRAs are constructed of ceramic material that has a high permittivity and low loss. DRAs offer some of the advantages like small size, simple geometric construction, and lightweight, and they are of low cost. So if we use DRAs, it gives results like wider bandwidth as compared to microstrip antenna. And DRAs support different feeding techniques like slot feeding technique, coaxial feeding technique when compared to microstrip antennas to activate the dielectric resonators radiating modes. And DRAs exist in different shapes like rectangular, elliptical, conical, hexagonal, triangular, cylindrical, and hemispherical. They exist in different shapes. The features of DRA are they offer simple coupling schemes to nearly all transmission lines. They are of low cost, and conductor loss, there is no inherent conductor loss, and each mode of DRA has unique internal and associated external field distribution. So in this design, we are using a metasurface. A metasurface is a thin metamaterial. It is mainly used to reduce the size of an antenna. So actually, we can't reduce the size of an antenna directly. If we reduce directly, it may lead to some degradation in gain, return loss, and they may change in resonant frequency. So without directly reducing the size of an antenna, we are introducing a metasurface, which reduces the size of an antenna. And also metasurface also used to increase the impedance bandwidth. And so mainly in our design, we are proposing a metasurface on the top of the DR layer, and we are using a slot feeding technique. With slot feeding technique at the bottom of the layer of the ground plane, metasurface having a metallic pad cell. So coming to our design. So this is our design, sir. So here this green color, this one indicates the ground, and this is the port, and this is the feed line, which slot feed line is used. And the bottom one, blue color, represents the DR. Here, to design a DR, we used Rogers material with relative permittivity 3. And here, this red color line indicates another Rogers material with directivity 10.2. And we use the metasurface material, and we divided the pad cells into regular triangulars. So here we divided into regular triangles. So this is the top view, sir. So this red color is with Rogers R030 material we used with relative permittivity 3, and this is feed line. We used slot feeding in this technique. And while if we given the simulation results as compared to the existing design and the proposed design, we got resonating frequency at 7.36 and in the frequency range between 7.16 and 7.52. And we are and our antenna works for satellite communications, 5G applications, and wireless communications. So coming to our simulation results, this is the S11 plot of our designed antenna. So we got so here M3 is a peak. We got M3 at 7.2424 at the gain of minus 26 decibels. So we are getting the S11 plot, that is the frequency range is between 7.09 and 7.44. And this is VSWR pattern for our proposed design. We got at M1, this is a peak, 7.2424. This is a radiation pattern of E plane and H plane for our design. And this is frequency versus total gain of the slot. We got it 5.4 like that, sir. And our antenna works in C-band. The frequency range of C-band is between 4 and 8 gigahertz. And our antenna is mostly omnidirectional. The dimensions of our antenna are length and width are 50 mm and 50 mm, and height is 5 mm. And the gain at 7.24 is 4.5 decibels, sir. So our main objective is to design a DR for wireless communications and satellite communications. So this is the literature survey we have referred, sir. So based on this literature survey, we have selected our design structure, and based on referencing all that, we have done simulations for everything, and we have selected frequency range. That's it, sir.
Okay, so is that all?
Yes, sir.
Okay, so few questions.
Yes,
First
sir.
of all, can you go to your SWR plot?
Sir, I can't hear you, sir. Your voice is.
Okay, so am I audible now?
Yes, sir. You're audible, but your voice is somewhat noisy, sir.
So the thing is, can you go to your VSWR plot?
Yes, sir.
Yes, this one.
Yes, sir.
So you mentioned the VSWR you have got is 0.847.
Yes, sir.
Am I correct?
Yes, sir.
What does that mean?
What does that mean, sir?
What is VSWR?
VSW, voltage standing wave ratio.
Yes, but voltage standing wave ratio means it's a ratio of the maximum voltage divided by minimum voltage.
Yes, sir. Maximum voltage divided by minimum voltage.
Yes. So if your ratio is less than 1, what
Yes,
does
sir.
that mean? So your minimum is more than maximum. Is it possible?
Sir, I did not.
Your ratio of a maximum by minimum is
Yes, sir.
less than 1. Does
Yes.
that not mean that it will be your minimum is more than maximum? So VSWR, what is the minimum value?
VSWR minimum value, sir.
Yes. VSWR minimum is always 1.
Yes, sir.
VSWR cannot be less than 1.
Yes, sir.
In case you should check these results, doesn't look correct to me. VSWR is never less than 1.
Sir, we'll work on it, sir.
Huh? Yes.
We'll work on it, sir.
So, okay, so that's one aspect. Next aspect is you said meta surfaces. Am I correct?
Yes, sir. Meta surface.
What do you mean by meta surfaces?
So meta surface means, so meta surface is a thin material, thin films which are made up of distinct elements that were created to overcome the problem faced by metamaterials.
Yes, so what is metamaterial?
Metamaterials, sir. Metamaterials are, sir.
Yes. Yes.
So, sir, they're artificial electromagnetic media that was structured in
Yes.
sub-wavelength scale, that was.
Yes.
And they provide some optical properties.
Yes. So meta surface
3D structures.
or metamaterial
Yes, sir.
has to provide a non-natural properties of the material. It cannot be a single standalone cell.
So metamaterials are 3D structures.
3D or 2D, whatever, it need to have a lattice. It need to have a period. It should repeat itself multiple times. If you are making it a single cell and you are claiming it's a meta surface, metamaterial, I guess you should check the literature. It's not the case. Okay, so DRAs are DRAs. So if you are talking about DRAs, they are DRAs. They are not metamaterials. Metamaterials definitely when you are thinking of a periodic array. So there should be periodic repetitions.
Okay, sir.
Okay. Okay. Yeah, fine. Yeah, so I guess you should work on these things, basics before because other thing is you need to check why whenever you are picking a structure, you should know why you are picking that structure. That should structure geometry should have some benefits. So work on that. Okay. Yeah. So thank you again for participating. It's a nice presentation, and if any questions from the audience, it is welcome.
So sir, our paper is titled as Design and Fabrication of Microstrip Patch Antennas using LTCC process. Giving the briefly introduction of LTCC technology, the LTCC is abbreviated as low temperature cofied ceramic. It is a technology which is used to fabricate different kinds of RF devices and etc. devices. So this actually uses some kinds of ceramic substrate sheets to be used for screen printing different kinds of metals which acts as the antennas and etc. parts. So the main advantage of this LTCC technology is that we can print embedded passives and etc. which cannot be possible in our regular PCB models and etc. Defining an LTCC device exactly means it consists of multiple dielectric layers screen printed on photo image, low loss conductors, resistors, capacitors, and these sheets are connected through wire holes, which will be tiny holes passing through all the sheets, which will connect all the sheets together for their conductivity. We can we can make different kinds of RF modules and etc. devices using this LTCC technology. So, sir, we made this project by using the help of the Star C labs available at the Bangalore. This is our project, and we used their fabrication center, the fabrication lab, to make these antennas, and we developed the design there itself. So based on their need for basic microstrip patch antennas, which were made by us there. They provided the substrate material called A6Me, which is a composition of alumina, silicates, and other substrates, which are mixed together with a composition specified by the Ferro. Ferro is the company which actually makes these A6Me sheets. And you can see the PPT, those are the basic properties of the sheet of A6Me. And we use the dielectric constant as shown 5.7 plus or minus 0.2, which is the dielectric constant which is used mainly in all the design calculations of the microstrip patch antenna. So briefly explaining about the LTCC fabrication process, we'll be having a green dielectric tape, which is A6Me substrate. And we first we design our required antenna, and we try to simulate it by using the HFSS software, which we all know very clearly. And after the completion and getting the results as per our requirement, we can go to the fabrication process, which will be started by wire punching, making the holes through the sheets as required for the design. And these wire holes were filled with the metals like gold, silver, and etc. for their connectivity between the layers. And our antenna design will be printed through a regular screen printing mechanism, which will be available as a machine at the Star C labs. So after this printing, all these sheets were stacked one on another so that it will be ready to get fired. And after stacking, it will be laminated and fired so that the final device will be occurred and it will be used for the testing purposes. So introducing about our antenna, we all know antenna, which is a device called transducer, which transforms an RF signal traveling on a conductor into electromagnetic wave in the free space. So basically, there are many kinds of antennas like wire antenna, aperture antenna, reflector antenna, lens antenna, microstrip antenna, array antenna, etc. So in all of these types of antennas, we preferred microstrip patch antenna because of its advantages like lighter in weight, lower in volume, low cost, low profile, and etc. advantages. Because it is the first time they are making an antenna in LTCC process. So we try to develop an antenna which will be low in cost and lighter in weight and easy to produce. So we preferred these microstrip patch antennas. And we made this antenna used for the X-band frequency. We couldn't tell you the exact frequency based on the StarC policies. They asked us to keep it on the secret itself. So we chose the microstrip patch antenna with some cuts in it. So these microstrip strip line feed is preferred as it is relatively simple model. And the cuts in the patch will be provided for the impedance matching, which will provide us a great result in the gain and bandwidth of the corresponding antenna. So sir, this is our HFSS design of our designed X-band frequency antenna. We made this by using ANSYS HFSS, and we used all the techniques and provided by the HFSS and designed and simulated it. And these are our simulated results, which gave us the S11 parameter of a gain of -26 dB and a VSW of 1.0. And you can see, you can also see the 3D polar plot and radiation pattern, which shows us the directivity of the antenna and the bandwidth of the antenna, etc. So after completion of the simulation, we actually, for the fabrication, we used AutoCAD software to design the Gerber files. So these are the different antenna Gerbers we created on using AutoCAD, which will be used for different layers. And this is our final fabrication result of the antenna. You can see the first picture. This is the antenna of X-band we produced, and you can see the size on the second picture. And the formation and alignment of wires can be viewed if it is connected clearly or not. All the sheets will be shown in the third picture, the X-ray view of the antenna. And after the fabrication, these are the hardware results which we obtained, which gave us the gain of this is the comparative study of simulation and hardware results, which gives the gain of -26 dB while simulation, and we got a dB of -22 while in fabricated antenna as an hardware result, whereas the VSWR varies by 1.09 to 1.15. Thank you, sir. This is our presentation.
Okay, so thank you for a nice presentation. So I'll have a few questions. First of all, so this stacking is made up of multiple such antennas, or these are made up of multiple different layers required for single one antenna?
Sir, for the fabrication of single antenna, different layers are used in stack. And basically, on each of these layers, we print what are required. For suppose on the top layer of this, for the top sheet, we print the 1 minute. We print this kind, or you can see in AutoCAD. This is the top layer, the first picture, which will provide us the basic patch and the patches used for the RF connector. And for the ground layer, for the ground purpose, we'll be screen printed with another metal, and this is the bottommost layer of the entire sheet. This will be the entire sheet, and it will be screen printed as the second picture. And based on the thickness we required for the firing without any warpages, we'll print the remaining sheets with these vias, and also these top sheet and bottom sheet will also be printed with vias, and these will be filled and stacked together. All the sheets are stacked together so that this vias and filled material will connect every sheet. And after the stacking, we'll cut this based on the our design. Like we see in the first picture, there are many antennas provided here. After stacking, we'll cut this as per the single antenna.
Okay, so now since you have fabricated this, so what if there is a slight misalignment between let's say 1% or less than 1% between two layers. So let's say your ground plane is slightly off in design with the top plane.
Sir, if the alignment is majorly displaced, then it will be a complete waste of money and the time of the Starcy labs.
It's all right, but I'm talking in terms of physics, what you are will be expecting.
Sir, the antenna parameters which are expected and which we obtained, the simulation results will be varied very much in this fabrication.
No, my question is again, I'll redirect it again. So, you have an S11 plot, return
Yeah.
loss. So that return loss will be broadened, or return loss will be sharper. Return loss at the resonance will be more or less.
Sir, the return loss will be more like it is in negative, right? If it is displaced, the return loss will be provided as minus 10 dB or something, which is not very good for an antenna. We must have
Broad or narrow? The same.
we'll get broad bandwidth, sir.
Okay. Yeah, so I can see some plus signs in your CAD. What are those?
Which, sir?
In your CAD, I saw some plus signs on the four corners. What are these?
Sir, sir, these are used for the alignment purpose. For suppose the basic sheets are first printed with these plus signs, which will be on standard itself, so that it will be used for us as the basic, what do we say, origin of the sheet.
So you use a 3-point alignment?
Sorry, sir?
You use a 3-point alignment?
We use a, it is just a 2D alignment, sir. 2D alignment.
But 3-point will ensure, because 2-point can be line, then 3-point will be ensuring a search. Minimum is required for a area. So 2-point alignment is up to a line. Then to go to 2-point line definitely will be for a surface.
Okay.
Okay, good. One more thing. Can you go back few slides? One more. No, back. No. Back. One more. Yes, here.
Yeah.
So, so you are feeling these holes through holes
Yes.
before the LTCC firing.
Yes, sir.
Okay. So what is the feeling material?
Pardon me, can you repeat the question?
Yeah, what is the feeling material?
Sir, that temperature range allows for the addition of low resistivity conductor material.
Feeling of the bias I am talking.
I couldn't understand you, sir.
Yeah, you were stacking now, so you had bias. I can see bias.
Bias, yeah, sir.
So bias feeling, what is the material I'm asking?
Gold, sir.
Gold you are using,
We use gold paste for the filling of bias for the conductivity.
not a copper one.
No, sir, not copper. Gold. It is preferred gold.
Do you know why?
Sir, based on its melting point and thermal conductivity, they use gold instead of copper and silver, sir.
Is it? Gold is used for something else, not
Sir, because of its low resistivity.
no. All are metal only. Copper has quite a good conductivity. If you require a low loss line, you definitely will always go for copper. The thing is, gold is chemically inert. Okay, so that's why gold is used.
Okay.
That's why your ornaments are mostly gold, because it takes a long time to get it rusted.
Yes, sir.
It preserves its originality much longer, so it doesn't get oxidized very quickly.
Yes, sir.
Yeah, that's why all electrical connects are with gold. Conductivity is much better.
Yes.
Okay, so thank you for answering all the questions and for a nice presentation.
Thank
So I would guess if you are also enjoying the sessions, other sessions,
sir.
please keep on attending sessions. So we will be closing only today, but next time definitely we'll be hosting it physically, at least try to do. So then definitely this will be much more interesting.
Sure, sir. Yeah.
Keep the good work and thank you for attending the conference. We'll, I think, close over here.
Thank you, sir.
Yeah, so thank you.
And telling about the reinforcement learning approach for autonomous racing platform is the most advanced technology in SRM. And moving to the introduction, we are going to design a new racing model which includes training and learning methodology. The training is divided into the training is based on the time price and the object avoidance. And the learning is divided into the word how to interact the model and how to learn to solve the model. You all know about deep learning and reinforcement learning, but deep reinforcement learning is the combination of reinforcement learning and deep reinforcement and deep learning. In normal reinforcement learning, we just take the median of images and the lab time is very less. But in deep reinforcement learning, we take the billion of images and the lab time is very low. We get the accurate model and precision model in this technique. And this is the model of the car. It will going to design. It is the 1/18th scale. Normally, we all know about the racing cars. It means the racing cars are so big. I mean, it is the small scale. It is the model of the car. This will be the design of the model of the car. It consists of the sensor and image processing techniques. The 4 wheels are act as the sensors. The 4 wheels are act as the sensors, and the black color chip is designed for the image segmentation of the model. And next one will handle by the microphone.
Okay. We can start.
So here right and the tab is not anything. It was quite learn from scratch. So when the tab technically it was going to learn from its own sensors and only comments. So this model by using the camera such as monocular camera, and we have used the real so it's a millions of data and millions of images and thousands of video data. So we are able to reduce the gap between the real world certain tasks and the autonomous tasks which we have designed. The model we have proposed consists of 6 steps. First, the plan is going to take which type of algorithm or model was going to design, and it was taking the next agent such as type of wheels and types of cameras and types of chips it was going to perform. Next.
Louder, please. Your voice is not loud. Louder, please. I spoke now. Is it louder? Yeah. That is speak loud.
Next, it was going to take. Next, it was going to take what type of step it was going to take, either left, right, straight, or backwards. So this step is called as an action, and it was going to check whether it should turn to the right side or the left side by using the state path. After the full lap, that means starting from to any point, it was going to observe the environment, and it was going to present. It was going to train its own learning algorithm by using the environment, and finally it reaches the. So the algorithm we have used in this difference is PIC algorithm, which is proximal priority algorithm. This proximal priority algorithm uses the optimization techniques and the policy techniques, which uses the reward functions such as positive reward or negative reward. The agent can able to get its positive reward if it does not go to the off track, and the negative reward will be given to the agent or the server if it goes to the off track or the runtime increases. These algorithms will have high accuracy when you're performing, when you're using the environment with different layouts. So the agent is going to start that was the agent, and it was going to take an action by using the type of environment it had, seen, and based on the environment, if the car is an outcome, it gives a reward, either the negative or positive reward, whatever it may be, it was going to reward for its actions. And that was the reward function we have designed. That was the reward function and we trained the simulation. It means it was going to run. It was designed in the form of a driver error methods. If it does not have any sort of successions in the app, it was going to let the model know that it was wrong procedure, and it was going to do the correct instructions so that it can able to perform better. We had used it, and the environment that we had used it. It was the first antenna we had taken 33 seconds to complete the track of code track.
Start there. Yeah, how can school?
We saved the models. We had seen the model.
Because coming and reading is not a presentation.
The evaluation time is 1 minute 45 seconds. It is the less time we found. Here we can see the 3 models: Bounty Racer 1, Webpatch, and EPIC-2022. The EPIC-2022 model is the best model. It may take nearly 1,000 iterations to complete the track. This is the percentage training. First, the average percentage is start from 0. That means scratch. Next, after 1 by 1 iteration, it will increase to 1,000 iterations. The percentage level is merely increased. and gets the better model. This was the average reward. This is the average reward function. The reward is based on the positive action and negative action. And finally, this is the conclusion. Our model will achieve 3 laps in less than 2 minutes. That means 1 minute 45 seconds. This is the future of deep reinforcement learning. We all know about deep reinforcement learning. The future is to avoid the curse of dimensionality and reward function engineering. The references are collected. And thank you for giving me the opportunity.
Okay, I have small doubt there. Please explain us what is the meaning of training. You have shown some curve, right?
Yes, sir.
Tell me what is the meaning of training? It's from market. Have marker. Marker. Yes, I used to have all this in the back there. Yeah, no. Okay, tell me, go to the previous slide. Where there is a called marker. Sorry, there is a called training. What is your methodology? Where's the flow chart? What's your methodology?
The methodology is proximal policy optimization algorithm, sir.
Where is the algorithm? You are designing the car for track for the autonomous driving, na?
Yes.
Okay. How many meter? What is the accuracy of your method? 85%. What is the speed of the car?
Speed of the car is
Have to check out.
can you sir?
What is the speed of the car?
Sir, basically it is not about the speed, sir. It may take the iterations in it. Once again, I will go the track.
See, last one. For car eyes, camera is the eyes. Okay.
Yes, sir.
I will take a video of this. Okay. Now what I'm doing, I am moving from here to there. See this? I am recording a video. Okay. My eyes are doing like this. Okay. So I record. You see me how what's the force? What's the force? Which is with my hands. You see me play my video. If I play my video, it will show like this. Right? So I want to track how many chairs in this video. How will you find out? The speed also there not. If it is very fast, if my hands don't move, you cannot able to find it.
So here we are not going to discuss about the speed of the cars because the car is going in
Is it an image or it's a video? You are working on video analysis now. You understand how?
We have just taken the track for layers. For example,
You misunderstood. I'm asking you practically. Okay, you practically fix the camera in the car. So the camera is recording. The recorded track just need to be processed immediately. Okay, then only you can take immediate decisions. Now you cannot train the model and get the output after half an hour. It's anonymous car, na? So what is the lag between the video and the processing time?
I think it between the 5 to 10 minutes.
10 minutes. So the car has to wait to take a decision after 10 minutes. You are saying that only, na? Second also very big. You understand? Suppose I am going here, I want to take a right cut. You are saying that you have to take a right cut. You are saying that you have to take a decision after 10 minutes. Okay. So my question is, under what speed if my car may goes, this is tracking is perfect. Optimal speed versus speed. Track is a track. Don't see. Try to understand. Track has a fixed size of the lane, fixed thing. If you see that all the tracks are drawn based on the Government of India's rules and regulations. Okay, the width of the track size that they are putting some paint, that is also fixed size. The material which is used, that is also fixed size. Okay, everything is programmed and it's fixed size. That was audited by the National Highway Authority of India. Then only this comes to commercialization. Before it comes to commencements, everything is audited properly. So if fixed some proper speed and fixed some proper track, then tell me how fast my car has to go so that my process video will be processed. Okay.
We will give full details in the final paper, sir. Our
Final
algorithm is based on the PPO algorithm, sir.
Okay, no problem. Show me the algorithm first. I want to ask you two questions. We are shown some algorithm of for iteration. Show me the plot actually. What is this plot? Average reward? No, I don't want this. Go to the training.
This is the percentage training, sir.
Go to the training. I want that training curve. Nice, what's your problem? Don't waste the time. Next. Stop here. Percentage training. It is the average percentage of completion while training. Model approximately covers after 1,000 iterations. The average evaluation per laps increase with the iteration as per the model get better. I want to know that what is x-axis and what is y-axis.
Sir, x-axis is the iteration period, sir. It starts from 0.
First iteration.
Yes, sir.
Second iteration. Third iteration. What is y-axis? Best model. You are saying 4 models. You are finding which model is best. What is the meaning of training?
So we have designed 2 types of algorithms. We have taken the best algorithm in there.
At a time you are processing the video. Suppose X is method 1 is one algorithm, method 2 is one algorithm, method 3 is one algorithm. These are all models. So you are training at a time all the 3 models.
No, sir. One of them.
Oh, misunderstood the presentation. And go to the first slide. First of all, the first slide itself wrong. There are a lot of problems. Okay, the flaws. Go to that. Go to the first slide. Yes. See, this is author's name, not this as a arrow mark actually. See, they are a presenter. See that this is by, this is the person. Okay, department of this. Suppose this is authors. Okay, author 1, author 2. Your next department of, next institute name. It should not be like this. Both are same institute now. Correct now? It should not be like this now. Suppose your name is first, second name, next department of AI and ML, and institute of this. They are like this. Correct now? So you are without any your supervisors you came from presentations.
No, sir. My HOD sir will help me for this presentation, sir.
Then where's his name? Huh?
The PPT and model training was designed by us, sir.
You know what's the meaning of a supervisor?
Yes, sir.
Fine, no issues. So first slide itself wrong. Okay. Next, go to the next slide. Okay, to next slide. Next. Proposed model. This is what is model actually? What is the name of the model? What is this model actually? This is normal scene and that.
Yes, sir, because the proposal model is the type of model we have used. In this model, we have used deep convolution networks.
Network or neural
So
network?
we have
Neural networks, convolution and neural
In the network in the CNN.
So we have shown the classification. What type of classification we have used?
Go to the next slide.
So that was the picture for the
Procedure of the study. Next. I'll have this algorithm.
Yes. Yes.
This algorithm is inside the CNN. CNN.
Inside the classification, we have used the algorithm. Inside the classification.
Inside the classification. So what classification algorithm? See?
Deep attentive
Attentive
convolution.
means? Attentive means? Attentive means?
The algorithm which takes the millions of data.
Attentive.
It is going to
Deep, I understand. First question, what is the meaning of deep?
it is going
No. You have to understand what's the meaning of deep, what is the meaning of attentive. Okay, inside this there are neural network. Instead of that neural network, you are going to use this algorithm. So something is gap is there. Okay, prepare it more issues. This is it's our duty. We have to correct it. Okay, fine, no problem. Dr. N. Krishna, sir, you like to ask any questions to the students? Dr. N. Krishna, Chaitanya. Sir, you'd like to ask any questions? Should be fine. No problem. Students, you'd like to ask any questions? Okay, fine. Go to the next slide. Where is the confusion matrix? What is the purpose of going for confusion matrix? Confusion matrix. Huh? What metric you are using actually? What is the cost function actually? Gradient descent is an algorithm for back propagation. What is the cost function? Are you using MSC? Mean square error, mean squared error? Or what's the cost function you're using? Okay? Don't come here. It's our duty to make you sure how strong you are, how depth you are. It's our duty. Okay? And thank you so much for the presentation. Okay, next presentation is by testing the accuracy of methods in a forecasting of stock price using the time series analysis. Is this? Okay, novel method of highly secure image encryption techniques. A novel method of highly secure image encryption techniques. Yes, please. Go ahead, please. What is the first slide first? Always you have to explain from the first slide. Who's going to start? You start first. Next, you have to do that. Oh, like that. Okay, now camera is okay. Good morning to all. My name is Musa. I came here along with my friends Abdul and Hashim. And it is a great and good to ourselves to you. We are pursuing the second BTech Electronics and Communication Engineering from Karnataka, Town. And that is our solution. And my topic is novel method of the highly secure image encryption techniques. First, I'm going to introduce introduction of the major challenges. Whereas these images are to be transferred and shared via internet. There are the number of methods available for the image security. The process of the converting the readable format to the unreadable format is called as encryption.
The process of information distribution is known as ciphertext. The process of retrieving the overall information from the ciphertext is known as the description. The process of studying the encryption and decryption is known as the cryptography. There are the two types of cryptography of the techniques. Here we use the secret key cryptography, where the key is known to the sender and receiver. The major challenges of the issues of the today's internet is developers are secure transmission. There is a possibility of changing the content of the image. That is, the method is also difficult, complex, just like the design very much.
Second topic is aim and research. In this paper, we proposed a novel method for transmitting the image, transferring the image over the internet. The proposed method is based on the original image to be sent, and the cover image is also called, as a reference image. There are three secret keys and password. Keys are passwords. It is a triple protection, and it is helped the three secret keys. These are passwords. The cover image is used to encode the pixel value into index value. After the image quality has been verified with the original image, the image quality as assessment. The process of method is very difficult to rewrite the original image from the encrypted image.
We proposed a work and introduced the image, highly secure image. We have to process the proposed methods. There are three of the cover image and original image and the three secret keys. Here we need of the two images. First one the cover image and the original image. This cover image is to be transmitted, and the original image is to be providing the security of the data image. Here in the inscription process, we have the two data image and the original image. And the original image is the helps. The original image helps to change out the values from the index values to pixel values to index values. Here we have both of them divided into two planes. There is the RGB planes, whereas the red, green, blue planes. With every of the image here we power of the red, green, and the blue colors. And long diagram will be explained. Inscription process. Data images are two types. Three planes: R plane, G plane, B plane. Cover image also three planes: R plane, G plane, B plane. R plane or data image or cover image or R planes are pixel value, data image is cover image, and find the index value in the cover image. Then G plane in data image, G plane in cover image also same. B plane of the data image, B plane of the cover image also same. And that one is one step. Another step is create secret key one, random data one, secret key two. Okay. There were RG planes, three planes ki three secret keys are allowed. That process is XOR process, and the inscription B plane, the G plane or R plane. Another description process also. In this description process, we have the encrypted planes and the secret keys. The secret keys is nothing but the passwords. The secret keys one and the random data. We have the XOR formula. This is one popularly used formula. This is used for the highly security purposes. Here we have the cover image, which is also known as the reference image. Here we have R plane dividing index values of R planes. And the encrypted of the G planes is nothing but the green plane. We have the two secret keys, that is the secret key 2 and a random data 2. Here we also use the XOR formula. And in the cover image we have used the G plane. This is nothing but the green planes. can change the index values. The cover image is the purpose used for the changing of the pixel values into the index values. Like for the cover image, it can be divided into the field. The field is nothing but blue plane. We use it for the XOR formula. Index. This one is the result of the encryption. This is the result of encryption. Result after the process. After the process. What do you think? What do you think about the encryption technique? Encryption. Result. What do you say? Another result. Results are result. This one is result. Results in encryption, sir. Results in encryption, results in decryption. Yes, sir. Next, sir. Decryption, sir. This is the results in decryption. Decryption or description? Description. Decryption. Decryption. You are saying description. Description means whatever after writing. This was description. This is decryption. Next, example. Images are used for data and cover images. Taking examples. Explain about the results.
The data image is purely original image. What do you do? Original image, data image. The cover image you change it. The data image change into cover image with using XOR formula.
Data images change it to cover image.
Yes.
Are you sure? Are you sure? Next. What is this?
Data image.
Taking examples. Data image and cover image. Taking examples.
What is that? What is the first line?
Excuse me, sir.
Yes, sir. Yes.
Excuse me, sir. Sir, let me clarify in this. Go back to the previous slide, please.
Yes, sir.
Yeah, this is the original encryption method where we try to transfer the original data image with the help of cover image.
With the help of cover.
Yeah, with the help of a cover image. What we are going to do here is that whatever the pixel values I'm having in the data image, I need to verify the same pixel value in the cover image. From the cover image, for the pixel value, I need to identify the index value. I will take the index value from the cover image. The complexity in this process is whatever the image I want to transfer, whatever the colors or the pixel values I'm having, all the different colors has to be there in the cover image. That is what is the challenging issue in this particular encryption technique. We have the three planes, R plane, G plane, blue plane, RGB. So for each and every plane, we are having one secret key. One secret key we are going to be using. That's why for the three planes, we have a secret key 1, secret key 2, and secret key 3. Along with that, internally, we are going to be using random number generator, where the random number generator is going to be generating the data based on the actual length of the data image. So this is what is basically the encryption method. What we are going to do here is that data is going to be split into RGB planes. For every plane, we are using one secret key, and we are going to be performing the most powerful operator called as an XOR operator. Though it is having some drawbacks, I'm not going to be bothering about it. Then this data image going to be converted into an encrypted data through a cover image. But we have not shown anything of that. What we are going to do here is that whenever it is an index value, the number will be usually a large value. So we are not going to be transferring any image after encryption. It will be purely a garbage data, like a huge numbers we are trying to transfer. That's why people cannot be able to understand the sender is going to be sending an image. That's an advantage. Nobody can identify this. This is an image. The sender is going to be transferring it to the receiver. That is what is a major advantage. Go back to the next slide. Yes. If we give any one of the password as a wrong, there are two scenarios. One scenario will be if you give any password as a wrong, it cannot be able to retrieve the original data image. That is the one scenario. You try to give any other cover image. In that case also, you cannot be able to retrieve the original image. That is the advantage. Why this is a novel method and the most powerful method is that it's very difficult to identify all the 3 passwords. There is no constraint on the length of the password, what type of a characters I need to use. That's why this is very, very powerful with the 3 passwords along with the cover image. Even the hackers cannot be able to identify. Still, it has to be tested. Some cases needs to be tested here. As far as we tested, it is providing very much security. Now, this is the case where we have given correct cover image with the wrong passwords. This is the scenario. Though the cover image is correct and the passwords are wrong, you cannot be able to retrieve the original data. Next slide. Yes, this is another scenario. I have given the same correct passwords where I have used for the encryption, but see the cover image. Cover image is not the original one what I have used. So you cannot be able to get any data image here. You cannot be able to get. That's an advantage. Next one. Yes. This is the third scenario where we are going to be getting that original data image only with the help of all the secret keys are correct and the cover image is also correct. Then only I'm going to be getting the original data image. This is the actual process.
Okay, fine. Thank you, sir. Thank you. Yeah, go to next one. Sir, actually, these people have to say that it's a simulation diagram. Nah? They are saying the result. Okay.
Actually, there is a block diagram where we are going to be getting in the lab.
Actually, go to the previous slide. Previous. This is a simulation diagram, sir. Simulink.
Yeah. No, it's not in the Simulink. It is from the lab user.
Lab view software. Okay.
Yeah, lab view software.
Okay. In the, my image encryptions are also performing using lab view.
Yes, sir. Both encryption and decryption we are doing in the lab itself.
Okay. Fine.
Except for the last one, we just try to compare both the before the encryption and after the encryption. Both the images are compared with the help of MATLAB. That's why we have quoted with the table.
Okay. So, but here you performed everything on lab view. All the processes are on lab view.
Yes, sir.
Super. Okay, fine. So actually, what is suppose the MATLAB if I'm using the processing of images, all those things take a long time. What about lab view? Is it doing faster? Or?
Sir, it's a very much comfortable, user friendly. We no need to write any sort of a code.
Okay.
Whatever there is, see here, sir. Whatever the diagram here it is indicating, whatever the logic I want to implement, simply it's just similar to the Simulink, but it is better than the Simulink.
Okay. First time I'm seeing the image encryption lab view. Generally,
yeah. Yes, sir. Most of the people are tried in the MATLAB itself. We tried in the lab view.
Okay. You can mention the slide. Okay. That's why I'm asking them what is this? Okay. Can you mention this is a Simulink based on lab view?
No, it's not from the Simulink. It's from the basically from the lab.
Lab view. Okay.
Yeah.
Go to the next slide. Go to the before. Scenario. Tell me, what is this SSIM? What is the meaning of this? What is the expression for this? Abbreviation or expression? SSIM. What is this? What is the meaning of PSNR? What is the expression for P? Peak signal to noise ratio. Okay, what is SSIM? Okay, fine. Sir, what is this actually SSIM?
Sir, it's a structural similarity index, sir.
Okay, so you are using a
sir, yes. So, here we need to get it as a we are going to be comparing after the decryption and before encryption. After decryption, the images are compared. This is the case. The structural similarity index it is indicating is almost matching with the 98%, because sometimes whenever you try to transmit and receive the data, some of the pixels are gets corrected. What we did in lab is we have looked to that image in the internal processing itself, and we have received the encrypted data, and we have again decrypted. So most of the data we can be able to retrieve in the decryption process. Definitely, whenever you try to transmit and receive and do the decryption process, sometimes there is a possibility for some damage of the pixels.
Super. So here we are trying to say that BSNR is 45, so that it is achieved is better, or what are the references from the BSNR?
Yes, sir. The problem is that we don't have any reference. I mean, there is no previous methods for this one. We are unable to compare with that. That's the problem.
Okay. Have you filed any patent? Is it your own method?
Yes, sir. It's my own method.
In the sense, your own algorithm.
Yeah. But people are able to develop, but the students are able to support for the development in this.
Okay, fine.
But this slide I have introduced. They have supported for the clarity.
Okay, so first one is it your method is algorithm is new way, and
yeah.
Have you found any pattern or something? Filed any pattern?
Pardon, sir?
Have you filed any patent or any published in this work in that?
No.
Okay, fine. So see, right now, the data encryptions, always that cryptography is always in the market of EPIC, right?
Yeah. Exactly.
This is one of the way for encrypting the data, and it may be encryption time will be very less, or the accuracy of decryption will be very accurate. So these two are the encryption decryption time should be less, and the accuracy of the encryption should be very more. Kind of. So if you find those kind of things, you can file as a patent actually. So
yes, exactly, sir.
Yes, you are
even I'm having 3 patents. Even I thought to apply this for a patent, but why don't I go for another patent? Let me give a chance for my students to go and present a paper in the international conference.
Okay. So file first a patent. Also, you already have 2 patents, right? So you know how to do that.
Yeah.
Always encryption is always cryptography in the market. So patent
yes,
is
sir. It's always a hot topic.
Yeah. So kindly go for it. Fine.
Sure, sir.
Yeah, go to the next one. I want to ask one question. What is the meaning of XR? What is the input to the XR? What is the output to the XR? XR is the operator. Operator. Powerful operator. Okay, what is the input to this? What is the output to this? Can you draw the truth table for XR gate? Okay. Actually, XR isn't just normal operator, right? It's just a, if it is the same input, 0 output, it is multiple, it's a difference in A. So, okay, fine. So, no problem. And go to the first slide. First slide. See here you can mention like all the students. So students are in the same club and in supervised by Dr. N. This actually go to the top. This has to go to the top. That should be perfect. See, sir, one corner your institute logo, another corner the SRM logo, or the conference of in the middle you can use the conference of electronics and
yes. That's a missing, sir.
Yeah, middle of that it is a method topic of that, and the bottom of it is all the 3, and top of it is so left side corner is your logo, right side corner SRM logo, middle of that is a conference name, and in the white part, middle of this is title of the paper, and below that the student's name. Last is your name supervised by supervisor. Okay, presented by.
Sure.
Paper title, next one is presented by student name, next one is supervised by, so your name. So this is the system, sir. And the next one, go to the next slide. Next slide. Next slide. Yeah, actually here also there is nothing but slide name. Okay, the next slide. Previous slide there is no title of the slide. So every slide title should be there. Okay, next go to the next slide. Here there is the proposed one. There is a called figure 1 shows. You didn't mention anywhere there is a figure actually. What's in the figure 1? Show me. Where is figure 1?
Yes. Actually, while we are enlarging that, the data has been deleted, sir.
Okay, here there is no figure 1.
This is the figure 1.
Okay. So you just write down here figure 1. Okay?
So problem is that the PPT has been prepared in a hurry manner because we registered on 15th. That's the problem.
So it's my duty answer itself. Fine. What are the previous one? Previous. What is the proposed work? Here you are saying something, right? Pixels or data hours, cultures, index values, where the values. If possible, in some ways, you can have something called flowchart, step by step kind of log around. Step 1.
Sure. Algorithm is also there, but we have not included that algorithm because we are not disclosing that the entire content here, sir.
Okay.
As you said that we are planning for a patent also. That's the reason we are not disclosing the entire content over here.
No problem. So you write down here instead of giving this much big paragraph, write down step by one, log around. Step 1.
Yeah. Sure.
Don't say then we can understand what's happening. Okay.
Sure.
It's a nice work. Thank you so much.
Thank you, sir.
So you want to ask some questions?
What is optimal value for SRM? Both input and output images are same. It should be what is the optimal value?
Sir, Krishna sir, one time they have some doubts. Krishna sir. I'm audible.
Even without encryption, if both input and output images are same, if you compare two images, what should be optimal SRM value? And what value you are getting? Why there is difference? You are reproducing same image and decryption. If you are getting same image, it has to be what value? There is some change rate 0.98.
Have any idea? Try to find no issues.
If both inputs are same, SRM value should be 1. Since you are using some data, you are getting 0.98.
Okay, fine.
Yes, so our paper is based on modeling of CTS/CDS thin film solar cells using SCAPS 1D. This is a new solar capacitance simulation software, which is developed no less than a year ago. So coming to the objectives, the main intention of this software is to improve the power conversion efficiency of the thin film solar cells, and also enhance the experimental production of solar cells and reduce the cost factor. The main motivation is that, as we all know, in the present times, the use of people are trying to move towards the use of unconventional energy resources, and also the recent coal crisis is a main example of this. So we have to find ways in which the energy can be effectively converted to the maximum potential. So this is one of the software which will help us to do so. The main absorber layer which we are using in this setup is CTS. This is a non-toxic and environment-friendly material, which is cost-effective and has an optimal structural properties and optical properties. It has 30% of theoretical power conversion efficiency, and it is a good and it has a easy and good processing method for commercialization. Now coming to the reasons for using thin film solar cells over the conventional solar cells. This thin film solar cells is a second generation solar cell, which is made by depositing one or more thin layers of photovoltaic material or on a substrate such as a glass, plastic, or metal. Thin film solar cells vary from few nanometers to few micrometers, much thinner than the conventional solar cell technology. These are some of the images of thin film solar cells. And coming to SCAPS 1D, this is a solar cell capacitance simulator. And the images are usually one-dimensional, or the images of the solar cell which will be modeling is one-dimensional in this software. And also the program was and the software was developed by the Electronics and Information Systems department by the University of Ghent in Belgium. So now let us have a brief look at the software. This is the startup panel interface, which I'll be even demonstrating at the end of the presentation. This is the main setup interface where we can set our solar cell, the buffer layer, the absorber layer, and the metal contacts. These can be set according to our problem, and all the conditions such as the spectrum of the light, solar radiations used, and the type of metal contact required can be varied using the metal function. And this is the main JV, or current density versus voltage characteristics. The measurements were carried out in the sunlight with a incident solar power of 1000 watt per meter square and a temperature of 300 Kelvin. The JV characteristics from this software, it mainly tells us about whether the simulation is working properly or not. And based on the JV characteristics, we can further look into other graphs such as efficiency or fill factor, etc. And we have mainly dealt with efficiency based on thickness. This is the efficiency graph which we have found for the absorber layer versus the efficiency. The figure shows the solar cell variation versus the absorber layer's thickness. By varying the thickness of the CTS absorber layer, the maximum efficiency which we obtained was 10.02%. This is the variation of efficiency by differing the buffer layer thickness, that is CDS. As the thickness of the CDS buffer layer increases, the efficiency of the solar cell decreases. The buffer layer loses photons due to the photon loss effect. This can be clearly noticed in the figure. The efficiency starts at a max of 9.6% and drops up to 8.1%. And this is a other reading which we have found using the simulator. This is the variation of fill factor of the solar cell with respect to temperature changes. We have varied the temperature from optimal and up to the breaking point of the device. We have varied from 260 Kelvin up to 380 Kelvin. And the efficiency and the fill factor are noted as follows. Now let us, I'll just present give a brief demonstration of the software. So this is the SCAPS 1D software. Here, it is a very good software where we can, it gives us the option of changing the working conditions. Here, the working point, temperature, voltage, and frequency can be set. We have kept it for the demonstration purpose. We have kept it at the default temperature 300 Kelvin and frequency 10 to the power 6 Hertz. And also we can choose the type of solar spectrum which can be used for the software, and we can test it in dark or light conditions. But since majority of the times the solar cell, the solar cell only works in the sunlight conditions, we'll keep it in the light condition for the demonstration purpose. And the solar cell spectrum is being selected. And in the action panel, we can select the graphs which needs to be used or the results to which is to be viewed. Here we have selected IV or JV characteristics, and we can set up the start and stop voltage. We have used a 0 to 0.8 voltage. And we can also select the number of points in the x-axis. Here we have set it to 81 points. By changing the number of points, we can get more accurate readings. And then in the set problem, we can choose the problem setup. Here the this is the solar cell problem which we have set up. The red indicates the CTS layer and the blue indicates the CDS layer, and the black lines indicate the right and left metal contacts. And these rays are the solar spectrum which we have selected. And the metal contacts can be varied by using the metal function. The metal function which we have used is 5, which is close to aluminium. But we can choose any material according to our problem by changing the metal function. And the CTS and the layer structure is mainly decided by the parameters which we set for each layer. For example, CTS, we can change the thickness, band gap. Majorly, the band gap is what most of the times decides the material's characteristics. So the CTS has a band gap of 1.21 and so on. And also the doping concentration can be set up, the donor density and the acceptor density. So accordingly, we can set the material, the type of material we want. We came to these values by going through several literature papers and the operational condition for each of the material, and whichever was and we tried different permutations and combinations, and which gave us the perfect IV characteristics. We went with that, and then we click on okay. So now let us just look at few of the graphs. So this has 2 types of settings: batch setup and recorder setup. In the batch setup, we can decide the layer which we need to demonstrate. Here I am sticking to the absorber layer, that is CTS, and we can demonstrate, and we can even select the parameter which we need to vary upon. So since our paper majorly concentrates on thickness, I'll be sticking to thickness, and we can vary the number of points also which we require. Here we have varied from 0.1 to 1 micrometers. And this is for the, so this batch setup is for the x-axis. And coming to the y-axis of the graph, we can set it to any of the parameters which we want to read, such as efficiency or fill factor. Our paper majorly concentrates on efficiency and fill factor. I've already pre-set up the efficiency element. And now let me demonstrate how the graphs will look. This is just the band diagram, current density and current density graphs. But the major graphs which we will be looking into is the recorder results. Here we can see the thickness, that is x-axis and y-axis properties. Y-axis shows the ETA, that is the efficiency, conversion efficiency, and x-axis shows the thickness of the layer selected, CTS layer. And so the efficiency increases for the absorber layer. And as we have seen in the presentation, this condition will be opposite for the buffer layer, where the efficiency will be decreasing. And the similar way I can even show the IV characteristics. This is the IV characteristics for each of the thickness which we mentioned, that is 0.1 to 1 micrometers. So we have kept about 6 the different thicknesses. So for each thickness, each condition of the thickness, a different IV characteristic is demonstrated with different colors. And below we can see the ETA, that is the power conversion efficiency, which we have got is 10.02% accordingly. And based on the this is one of the demonstration which I made. And similarly, we can demonstrate other parameters such as fill factor, and we can even vary. And I showed for the absorber layer. Similarly, we can show for the buffer layer parameters as well. Thank you.
Okay, so I'll be talking about comparative analysis of advanced low power, that is using Cadence Virtuoso. So Cadence Virtuoso is nothing but a simulation tool for designing digital logic circuits, implementing the VLSI techniques for different circuits that we have in the domain of digital circuits. So the contents that I'm going to go through is, I'll start with the introduction, then the literature review, then the objectives of our research, and then the methodology that we used, then design and working of the proposed full adders and also the existing ones. And then we will compare the results that we have got compared to what is already existing, and then finally conclusion and differences. So to introduce my topic, it is based on VLSI. So if I go by the definition of VLSI, it is the process of creating an IC by combining millions of transistors onto a single chip. So on the right top, you can see flow chart. So any system that we have, it can be broken down into complex units, and then those complex units will have a simple components, and then they will have a certain logic that they work on, and then the logic, to implement the logic, we need a particular circuit, and to build a circuit, we use silicons and electronics. So that is how we go by when we are designing any system based on electronics. So here I'll be mostly talking about the circuit part of a logic that is advanced full adders. And so to talk about the full adders, a basic full adder is the one which has 3 inputs and it produces 2 outputs. So it will have binary inputs, A and B. So and yeah, also to mention, this is a 1-bit full adder. So it will have 2 inputs, A and B, based on which we will get a carry out and sum. And also when we go for the next, as we go on with the process of adding, we get a carryover as in normal additions that we have. So that's how the whole full adder works. So we have different methodologies and different conventions that we use to design the circuits. So since I'm talking about digital logic circuits, they mostly comprise of CMOS and bipolar BJTs and bipolar junction transistors, then BiCMOS, which is a combination of BJTs and CMOS. So when we are talking about VLSI industry, it is very important to talk about power dissipation, since we are combining millions of transistors on a single chip. So the power dissipation is huge. So we have to always try and reduce that. And then propagation delay time. So as we add more number of logic components and devices, the time it takes for the signal to propagate through the entire system goes on, like it increases. And also, like it is not only dependent on the the number of components that we have. It can also be due to doping and impurities that we have in the semiconductors. So power delay product is nothing but the the combination or the product of power dissipation and propagation delay time. So we always try to get a good power delay product for our circuits. We can have a good power dissipation, but if we have a bad propagation delay, then it might not be of use in every application. Maybe it has a particular application, but not for all the applications. So these are the literature reviews. So most of them are based on IEEE transactions. So these are the papers that we went through to decide which circuit or design we should go for to implement our own idea, to implement our own novel design. So these were some of them. I'll discuss about them in future slides. So these were some of the design names. So hybrid 3, hybrid 5, and hybrid 7. I have given the reference in the presentation down below. So these are the full adders with better average consumption of power. And then we had hybrid 7, which has a better propagation delay, and hybrid 8 and GDI2 full adders. These also corresponded to better propagation delays. And then hybrid 7 was the best out of the hybrid design. So we have different designs. We hybrid in the sense we use all the topologies that we have, or all the different kind of devices that we have in electronics, like GDI, CMOS, fast transistors, and transmission gates, etc. GDI is basically a CMOS, but here what we do is, connect the bulb to the source and the drain, so that we can utilize all the three the inputs, three sources as input. So source, drain, and gate also act as input, compared to CMOS, where only gate acts as a gate and source act as an input, and drain, at the drain we get the output from the resulting voltage at the gate of the CMOS. So our objective was to implement a novel design of advanced full adders and simulate using cadence virtuoso at 45 nanometer with enhanced parameters. So we wanted to get a good power consumption, propagation delay, and power delay product. So you might have a question, why 45 nanometers? So the cadence virtuoso, it is a commercial tool, and the license costs a lot. So what we had access to at our university was at 45 nanometer. So to get further down the chain of the transistor size, we need to have a better license. So we could not avail that on time. So we stick to 45 nanometers for our design. So this is our conventional full adder, where if I show the truth table, so this is the sum and carry that we are trying to get as outputs from our logic adder. So if you see the first part of here, the sum acts as XOR and XNOR, combination of XOR and XNOR gates. So XOR is basically for similar inputs we get 0, and for dissimilar inputs we get 1, and XNOR is the opposite. For similar inputs we get 1, and for dissimilar we get 0. And the carry acts as and or combination. So here we have a conventional full adder. So as I said previously, that sum will be a combination of XOR, and our Cout will be a combination of and OR gate combined. So PTLs are same as CMOS, but what we do here is we try to reduce the number of gates that we have. So logic gates, or logic transistors, sorry, not the gates, the transistors that we have. So conventional CMOS logic design might have 4 transistors, but in fast transistor logic we can probably implement it with 2 transistors, depending on which function we are trying to implement. And then we have transmission gates. So transmission gates, again, it is the logic output is basically whatever control we give. So we have one input as A, that will be here, and we have a combination of NMOS and PMOS with the gate acting as controls, and the combination of the drain here will be the output. So always the logic function for a transmission gate is whatever the input A and into whatever the control that we have. So if we have control 1 and output input A is 1, we will get B as 1. So something on that along that line. So this is about transmission gates. So mirror based design, again, they offer low power consumption and driving capabilities as compared to adders mentioned in previous sections. So this adder works on modified logic, in which carry out is utilized as input to get output sum, compared to conventional designs. But here what we had was the number of transistors that are there are quite large compared to the designs that we have considered. So they have this has 28, and the ones that we have considered have around 20 transistors. So the first the circuit that we selected, full adder circuit, was hybrid 7, because it had overall better TDP, that is power and dissipation product. So so if I go to the circuit here, you can see several modules here. So as I mentioned earlier. On the top here, you can see the carry. Sorry, yes, this is the carry. Module 1 and module 2, they basically give out the carry, and module 3 and module 4, they give out the sum. So here we have used transmission gates, pass transistors as a combination. And so what happens is, if we give an input A, so we have 3 inputs, A, B, and C, and 2 outputs, carry and sum. So when A is 0, then we get output as 0. But if A is 1, then we get output as B, which is basically a combination of here and OR logics to implement the entire CN, the part of the circuit. So basically, this whole module is and this whole module is OR. So together they combine and give out the carry. And similarly, so similarly here we have module 3, which is this actually whole combined is module 3, and this whole combined is module 4, along with the transmission gate and pass transistor logics. So they act as XOR and XNOR, and they give out the sum. So this was a 20 transistor full adder design. So there are 2 types of design again, with low transistor count and high transistor count. So this is a high transistor count. So the advantage of high transistor count is that we get a full swing output. The output is much more stable compared to what we have with low transistor count, because of many stray capacitance and other resistance and time constant delay problems. So that is the reason that we usually prefer the high transistor count compared to the low transistor count for if we need a better output. So this is the transient output for the existing design that was already there. And this was the power dissipation. I have a comparative chart at the last, so I will discuss it over there. Then the second design, this is the proposed design that we proposed. So what they had done was they had 4 transistor XOR gates. So we just tried to reduce the number of transistors wherever we could. So we came up with a design of 3D XOR gates and implemented the some part or the some logic part of the circuit to get a better performance out of the circuit. So we use 3 transistors to make the XOR and the XNOR gate. So the result you can see, if I compare the 2 graphs, I think I should have a comparison. Okay, I haven't compared them here. So yeah, so here you can see the sum part. It is very unstable, or we can see we don't get a full swing output here. But when we compare our design, it is much more stable, and we get a proper full swing output. And the second design that we considered was a low transistor count, or 10D GDI full adder. So here again we follow the same principle and try to, here we utilize the design of XOR and XNOR for sum and the carry. So what this technique offers is a full adder with significant less number of transistors. So the existing GDI based adder, there were 10 number of transistors with less power compared to what we had with the 20T, obviously. So here we have again tried to reduce the same the XOR and XNOR logic by using 3T transistor gates. Transistor gate for XOR and XNOR compared to what they have. So initially they had a 4T XOR, and so we tried to use the same methodology and replaced it with a 3T XOR. And then we have mux 1 and mux 2 to get sum and carry. So the function of mux is to basically overlap the 2 incoming signal that they receive and give out sum and see out in this circuit that we have here. So this was the transient analysis. Okay. This was earlier. This is based on the existing one, so that we have that we selected during the literature review, and our circuit has. This is our circuit. The transient responses. So you can see again we are getting a much better output. Obviously, like it is not full swing comparatively to the 20T transistor, but we are able to eradicate most of the problems that we had with the 10T. So since we have, in 20T, what we did, we reduced the number by 2. So we have 18T transistor full adder that we proposed, and here in this case we have a 90 full adder that we have proposed. Yeah, so okay, here we have the comparison. So you can clearly see the full swing. Here it is comparatively less, stable, or we don't get a full swing output here compared to what we have here. And again, same for GDIs, if I can compare the two of them. So again, here we can see overshoot and undershoots, and same here, but yeah, it is much more stable than what we have compared to the previous or the existing models. So these are the power and delay consumption, comparisons. So initially hybrid 7 had 20.28 into 10 to the power minus 6 or microwatt, or here we have 50 nanosecond delay, and then the PDP is around 1.4. And so overall, if you see, we have reduced the power as well as the delay for hybrid 7, and hence the PDP has also reduced. And but for GDI, we were able to reduce the power, but we were not able to get a good delay. So obviously, we will not be able to use it in every application. But yeah, in a application where we need less power but delay can be compromised, we can use this, this methodology or this circuit that we have here. Yeah, these were the references. Thank you so much.
Yeah, thank you, Anand. Thank you, Anand, for giving this topic, low power and high speed opposite full adders using GDI and hybrid designs. So can you, I have one question. Can you go back to your comparison table?
Yes. Yes, sir.
So you have implemented this GDI and hybrid designs, right?
Yes, sir.
For full adder circuits.
Yes, sir.
So, like generally, how you are estimated this delay?
So this is, so in Virtuoso we already have calculators here. So we use the calculator to get the delay and power.
Is it the accuracy? It's getting perfect in that Virtuoso cadence tool?
Yes, sir. It is an industrial level tool. So whatever accuracy we have, it is quite good with cadence Virtuoso.
What about power?
Yes, sir. Same with the power.
Power also is giving there.
Yes, sir.
And okay, that is fine. Can you go back to your slides? I want to comment on like when you are going to present, you're giving presentation. There is no like in that slide, like whatever the circuit you are showing, there is no name of the circuit. So you have suppose if you go back,
okay.
Let's say this is circuit. I'm wondering like what circuit?
Okay, so what I did was I had mentioned it in the previous slide, and then I followed it with the entire circuit.
So you should mention this is a 90 GDI pull adder, right?
Yes, sir.
Diagram. Similarly, the previous one.
Yes. So yes. So here we have 10T GDI.
Yeah. I'm wondering like when you're presenting this slide, I'm counting the transistors. Based on that, I'm understanding.
Yes, sir.
So you should mention on the slide itself on top side. This is 10T 90 pull adder like this. This is just one comment on from my side.
Yes, sir. Thank you, sir. Sorry that went unnoticed.
Okay, thank you.
Thank you, sir.
Next, we have one more presentation. That is topic title on modeling of CU2SN-S3/ZNS based thin film solar cell using SCAPS simulation tools. So please let me know who is there for presenting this title of this talk.
Sir, it's me, Tirtha.
Yeah, so just I'm giving this sharing option to you.
Sure.
Yeah, now you are the co-host for this presentation. Please share your presentation.
Yes, sir, I will be doing it. Please let me know if you can see my screen.
Yeah, it's visible. Please make full screen and please go ahead.
Okay, thank you. Even before I come to the point where I'm talking about the entire presentation, I would like to say that this is built, we are the same co-authors for the previous paper that was presented in the beginning. So it's going to be built upon the same logic. So coming to the topic name, it's called Modeling of CTS/ZNS-based thin film solar cell using SCAPE simulation tool. So it's been presented by Sabina Rahman, Tirtha Vai, and Diptoshi Roy. So now, when we talk about solar energy, it's very much necessary in today's day. Talking about the petrol prices, like even before coming to the conference, I'm sure, sir, you and all our other friends here were checking the petrol prices when you're filling your petrol or anything. So it's very much necessary to keep an eye on what the energy resources, which is providing our day-to-day necessities. So with the war and economic downturn, it's very much necessary to choose for an alternate source of energy, like renewable energy sources, which are freely available in our universe, and also they are non-taxable, so they will not be varied with respect to the economy. So is what we are trying to think. So but when you look at the present range of how the production is going on, so you can see that in the graph that we have here, which is a source from an International Energy Agency, that is just 9% of the renewable energy that's produced in total is coming up to the solar, which is very less when compared to the coal or oil or other sources of non-renewable energy sources that are being used to generate energy and electricity. So it is, and that's why we think that solar energy is very much necessary for the energy production. And one such, the modern changes that's taken place in this field is the thin film solar cell. It has been here for a while, but the problem is that they're based out of silicon, and the thickness can go up to around 200 micrometer for their viability in the commercial use or whatever industrial use that they have. So, and we can also see that in the recent times, there is actually the need for reducing the cost of this solar energy. So if you're thinking about silicon based solar cells, they are expensive even till date. So if you want it to be used full-fledged, the most important thing is reducing its costs. So you can see the cost per generation, electricity generation from different sources, and you see that the solar PV is still very high. So, but in the recent times, it is reducing by around 82%, but how to reduce it even more when compared to other sources? And that is why we have come up with this solution of using CTS and ZNS based thin film solar cell, because there are these materials that are used with compared to CIGS, which is generally used by people mostly, is that it is abundantly available in the it's available here in the nature. And also our main aim is to use SCAPE's 1D software tool, because the reason is by using the simulation tool, it is easier to vary different levels of the wafer level thickness and other parameters easily than experimentally building it from the ground. And this whole work mainly aims in providing data to the experimental scientists, so they can actually create or synthesize these materials in the lab with much more efficiency, with the values already readily available, than to experiment it every single time. So this is the proposed cell that we are talking about today, is the CTS as the p-type absorber layer and ZNS as the n-type buffer layer. So usually in thin film solar cells, we can add much more a lot more layers in between, like the window layer and window layer for increasing the efficiency. And but here we are going to speak purely only about CTS and ZNS. The reason is to study their parameter and their variation with respect to the nature outside. So, and also the reason why we chose CTS as ZNS is that that's non-toxic, which is very important, and environmental friendly. And also the low cost when compared to other materials like CIGS, because the production here can be done by the chemical process as well. So it is much more efficient to use these materials. Also, the absorption coefficient is really high when compared to CIGS and other silicon-based photovoltaic materials. And then CTS has a tunable optical band gap. So by various processes, you can actually change the band gap from around 1 electron volt. It can be raised. So, and also it's easy processing methods, as I mentioned before. And coming to the literature survey, this becomes very important for us because one of our authors is Sabina Rahman, which is who is our third author who we refer for literature survey, who has done the same work, but experimentally they built this solar cell with CTS and ZNS, but experimentally they achieved efficiency of around 0.5%. But we have built the same on simulation tool, which has shown a higher efficiency of around 6%, which is a drastic change. So if we have to every time, if we have to go from 0.5% in the lab to keep building it, it becomes very inefficient, and also the cost can go up very high. So by using this tool, we can say that it's much more easier to increase the efficiency for commercial viability. So this is the Scapes 1D software. One of our co-authors in the previous paper, Balwant, already explained this, and it's a very efficient software and open tool software. So you can see that you can have various working temp points that you can use for it to operate, and also dark and light condition. So dark and light condition plays very important role as well, because generally solar energy is only produced, the energy from solar cells are produced only in the light condition, but here we have also studied in dark condition what is the process that's happening, or is there any way that it can be made efficient. So I will not be talking more about the software because I'm sure you're already familiar with it by now. So here the left contact and right contact. Usually right contact is used as molybdenum, and left contact here we have kept it as the aluminum according to the properties, electrical properties. So you can see that the results is firstly it's the JV characteristics in the dark condition that we have studied. So you can, and light condition. So in the initial, when you can see that the short circuit current is around negative. The reason for that, with the increase in voltage, the reason for that, it's in the dark condition. So there will be a very small value of current due to the minority charge carriers that are present. But with incident of light, you can see that the efficiency also increases. And then coming to the effects of the absorber layer thickness versus the conversion efficiency, this is very important because this is with respect to CTS. So you can see that with the increase in thickness, there will be an increase in efficiency, but at a certain breakpoint, the efficiency remains constant. So there is a reason for that. Firstly, why it rises is the minority carrier diffusion length rises together with the absorber layer thickness. So as it increases, so this basically indicates that the photon induced electrons with longer diffusion lengths are created in this p-type absorber layer, and longer wavelength photons may be captured by this absorber layer, and it will attract more electrons to produce this electricity. And as the depletion region expands, at a certain point when the absorber layer thickness increases, the electric field produced by the depletion layer makes it easier for electrons to drift towards the n-type region. And in the next part is the absorber layer thickness. We have also studied with respect to the short circuit current and also open circuit voltage for this, how the absorber layer thickness parameter is going to behave. With the increase, you can see that with the increase in thickness, again, the current increases, but at a certain point, that's a break point, it will become constant. So this is because excess photo-generated carriers created in traveling through this region, like that junction, will have a higher probability of recombination and will contribute to very few photocurrents. So that's why the JAC, the short circuit current and the open circuit voltage will remain constant after a certain point. So you can see that it's just 1,000 nanometer thickness. So this is with respect to the open circuit voltage. And next, we have also studied the fill factor effect with respect to the absorber layer thickness. So you can see that we have achieved around 50% fill factor efficiency. And the source for this fill factor is basically the strong electric field that is formed across these absorber layers. So, and also the temperature plays a very important role in operation and efficiency of any solar cell, because it can neither operate in very cold or very high temperatures. So you can see how the temperature varies. The efficiency varies with respect to temperature. So at very low temperature, there might be higher efficiency. That is at a certain point, not at very low. But as the temperature increases very high, the efficiency decreases drastically. You can see that changes from 0.8 to 0 almost, and it's that is no efficiency is produced at very high temperatures. So an optimum range of operation temperature is what we have verified, and we have investigated it through 260 Kelvin to 400. So basically what happens is when the operating temperature increases, the electrons in the solar cell will gain a lot of extensive energy, but instead of like it contributing to the electricity generation, these electrons will become unstable and recombine with the holes before the carriers could even reach the depletion region. So that is the main aim. And also this, you can see that this is a variation with respect to fill factor and temperature. Here also the same kind of behavior is observed, that with increase in temperature, that drastically there will be a fall in efficiency. So these are our references that we have taken up during our literature survey. And yes, thank you so much. That is with it. And so we see that we have achieved around 6% of efficiency. We could see through the graphs. Thank you so much.
Thank you, ma'am. So I have some few questions. So
okay,
the first one is like you have optimized P-type and N-type material, that is ZNS and PTS, right?
Yes.
So can you a little bit explain about like how you have optimized for getting your the efficiency, like the maximum efficiency?
So generally when CIGS materials and all were used, as I said, 200 nanometer is the thickness that they have used to, commercially prepare thin film solar cells. But we have come up to around 0.1 micrometer of thickness for CTS and 2.2 micrometer. So if Balwant, could you, is it possible for Balwant to show it in the software? So we have it simulated, that's why. We can show you the values of the materials that we have used. So those are how they are varied.
Okay. And one more thing, like you have characterized. So what are all the possibilities are there characterize this solar cell? Like I've seen only current versus IV characteristics, and one more thing, thickness versus J. Like,
yes,
is there any other important parameters? These are the sufficient for to know about our solar cell, whatever we have designed?
So for solar cell, there, as you said, the absorber layer as well as the buffer layer, both are very important. But we are showing here in this paper only with respect to the absorber layer, that is CTS. But you have to study the same parameters for these buffer layer as well, which we have done, but are not in this paper because it will become a very huge thing. So we have done open circuit voltage and short circuit current, fill factor, temperature variation. All that is there in this paper. So you can do the same parameters as well for the buffer layer, which those values also, when you try to understand, the efficiency will be more.
Last final one, the solar cell dimensions, you have characterized with the thickness, right? And
yes,
whatever I have seen the characteristics of IV, so that y-axis is per centimeter square, like whatever you got, can you go? I think the presentation is stopped sharing. Okay, so I have in the IV characteristics.
Is this what you're saying, sir?
No. Before that, there is one more IV characteristics. Is there? Yeah.
This is the JV characteristics of CTS solar cell at dark condition.
IV characteristic, yeah. So here, so it's milliamperes per centimeter square.
Yes, sir.
Per centimeter square means.
This is the short circuit.
This is current density, actually, sir. This is the density.
Density, yeah. So the density you are getting according to the dimensions of the solar cell. So is it the dimensions? It is in centimeter square, or that area what you have considered for that particular the probing?
That area, whatever you have considered, that one only it is, sir.
So is it not giving the exact, like whatever the dimensions you followed the solar cell, like complete dimensions, like the length and width apart from thickness?
In this particular tools, I think we are not able to do that. But
when it's only one dimension.
When we'll do the actual experimental, because sir, I'm Dr. Sabina, so I did the work in the experimental. So I got efficiency is 0.5%, and I have used around thickness of absorber layer is we used around 350 nanometer, and we did not achieve the good efficiency. So my future work to work in this particular area as an experimental basis. So I just wanted to explore these particular tools, and we have just saw actually. As your absorber layer, it is going to around 100,000 nanometer. So it is giving quite good efficiency. So it's just a giving the good inputs to the experimental people, actually those who are doing this, because basically the thickness optimization we will do using trial and error method. So that is, yes, sir.
One thing, can you go back, ma'am, the structure?
I'm sorry, let's go back. Structure of the proposed cell, is it, sir?
Yeah, it's a simulated structure. Go to this, not this.
Next one. Yeah.
Here, like you have mentioned, like in the abstract itself, you have optimized P-type material, that is CTS material, right? So, like whatever the resistivity parameters you have optimized, or any other parameters, particularly like CTS P-type material.
So they have to optimize this carrier concentration, band gap. So in these options are there, actually they can, that whatever CTS properties are there, the material property, so those value only they will give. So that value they will get it from the literature itself, and they in that particular simulation that window is there, they will give the each layer, this is my carrier concentration, this is my band gap.
I understood. Like whatever you are looking for that efficiency and the filling factor. So
Yes,
what
sir.
you want accordingly, you have optimized here, or based on our applications, you have to tune those parameters. Like whatever you have, you tune efficiency and filling factor with that API, or we can also like improve our efficiency according to our applications. We can tune all these parameters in this.
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
So that's what I said. You can add other layers here also. As you can see, that we have just showed you this absorber layer and window I mean the buffer layer only, but you can add window layer here, and there are around 7 semiconductor layers that you can add to improve the efficiency. So the more the number of layers, at a certain combination of all these layers, you will achieve a very high efficiency. But here we are studying only with 2 layers of the semiconductors.
Correct. So that's why I'm wondering, like you have done with only 2 layers, and you made thin film solar cell, and that whatever film factor and the efficiency, you are satisfying with that parameter, or if you want improvements, you have to add some more layers here to proper tune. That we can achieve it, right?
Yes, sir. It's with respect to how we want to apply it with the application. We can add many layers and improve the efficiency as well. But for this was the highest that we could see for this combination.
Okay. Thank you. Yeah, Kirti, please go ahead.
Okay. Good morning, everyone. I am Chandrakirti Potina. I'm a second year MTech VLSI student from KL University, Guntur. And our title today is Design of Low Power Phase Lock Loop. I'd like to first introduce what phase lock loop is. Well, when we think about phase lock loop is usually considered as a component, whereas it is a system. It is a system that has multiple components, and the main purpose of using a phase lock loop is to synchronize an input signal and its output signal, where the input signal is called a reference signal, which we give, and it should synchronize the output. The output of the phase lock loop is given again as an input to the phase lock loop in a negative feedback manner. So why should I be concerned about phase lock loop? If we have a question as such as why should I be concerned, or why should I even care about a phase lock loop? Phase lock loop is used in diversity of applications, from modulation to demodulation to recovering a signal to generating a clock to using in radio frequency applications to wireless communication to It is almost used in every SoC or a system on chip today. And coming to the low power section of the low power phase lock loop, we could question again, why should I be concerned about low power? Today, in all the applications, we need compact devices. We want our batteries to stay long. We want it to perform well as well. When you want a high performance, we are increasing the density of transistors in applications, whereas we are decreasing the size. What happens when we decrease size is they produce a lot of heat. So, and they consume a lot of power as well. When we're increasing density, that also leads to increase in power. When we reduce power of each individual component, it tends to consume low power as entirely as a system. Also, because the size is getting smaller, there's also leakage power. And because we want high performance, so we're increasing density. So this is exactly why we should care about low power. When we talk about, so objectives of these paper are to decrease power as well as decrease log time, but increase efficiency overall of the system. Going to the components of PLL. PLL mainly has 3 components, I would say: phase frequency detector, a low pass filter, and a voltage control oscillator. But here we are adding a charge pump as well as a frequency divider. Going to the phase, this is a block diagram. This is how it is connected in a loop form. The PFD is connected to the charge pump, and PFD together with the charge pump, we call it as an error detection component of the loop. And there is a loop filter or a low pass filter, and there's a voltage control oscillator, whose output is again given back to PFD as another input. And this is how it forms a loop. Okay, coming to the working of PLL, it has 3 different states: free running, capture, and phase lock. When we do not have any input given to the PLL, it is in a free running state. As soon as we give the input, it starts generating frequency and adjusting. This is called capturing phase. When it finds its lock frequency, it tends to lock and produce the same signal that it matches to the reference signal. This is called the lock state. When we talk about phase frequency detector, what do we mean by phase? Phase is nothing but an angle, 360 degrees. When we give 2 signals, since we're giving 2 inputs to the phase frequency detector, it compares these phases and frequencies as well and gives the output as the difference between these 2 signals, difference in the phase. When we're talking about phase difference of 2 signals, either one signal is leading or one is lagging behind the other. This is called phase difference. So phase frequency detector will keep on working until such that it produces a constant duty cycle where the frequency and the phase both should be the same. Phase frequency detector has here we're using 2 D flip-flops and 1 AND gate. One D flop, first D flop's input is clock reference or a reference signal, and the second D flip-flop has the input as VCO's clock VCO. That is what output of the VCO I'm calling as clock VCO here. Frequency of clock REF is always higher than frequency of clock VCO. So up signal, the output of the first D flip-flop almost spends a lot of time at a high state than the clock VCO. As soon as the rising edge of clock reference is maintained until the first rising edge of the second signal, second D flip-flop, that is clock VCO, also reaches the rising edge. So this how it translates into a practical application is such that VCO is driven higher, the input of VCO is driven higher, causing an increase in frequency of a clock VCO. So this output is a reference of, is a series of positive pulses. After this, it goes into the charge pump. Charge pump has phase detectors. Outputs are given as the input to charge pump. where here it converts the frequencies into a low frequency signal. What happens here is the VCO will keep drifting as much as there are phase errors and there is a difference between the first two inputs. What happens over a long period of time of this cycle is, as long as the loop keeps running, there will come a time where the output becomes a subharmonic of the clock frequency signal, which is obviously a low frequency signal. So this output is given as a low frequency signal. This is why after charge pump we introduce a low pass filter. Because the subharmonic is a low frequency in itself, the low frequency signal part of the signal stays behind and the high frequencies get filtered out. This low frequency is given as an input to the VCO, voltage control oscillator. As the name suggests, it is an oscillator that is controlled by voltage. An oscillator takes this voltage as the base, and it produces and it generates a frequency according to the voltage. But here we're using a current starved voltage controlled oscillator, which is 3-staged. Here we have current mirrors, 3 series of current mirrors, as well as inverters connected. What happens in a current, why are we using a current starved VCO is because it relatively offers low resistance. That is why it consumes less power as well. We've taken a base paper. So here we are comparing the existing and the proposed design, how we've changed the design and the waveforms as well. After the current starved VCO, then we have the frequency divider. The frequency divider design is here again. A frequency divider, why we're using a frequency divider is, for example, let's say we want a 200 kilohertz of an output, but we are giving 100 megahertz or a 10 megahertz. So frequency divider reduces the frequency into by 50 or by 10, whatever by n, that n number is, and it keeps on looping such that we get the desired frequency as the output. This again goes back to the phase detector and it keeps on running. The phase lock loop will keep on running as long as it finds its constant stage, and the clock reference and the clock VCO, both the signals are in the same phase and in the same frequency. The amount of time it takes to lock the frequency or find the lock frequency such that it matches both the frequencies is called lock time. So that also we have compared and reduced here from the base paper. And the base paper is this Ohio State University's paper. And I'll end my presentation here. I thank Pradyut Sankhi sir and Swagata ma'am for organizing this and giving me an opportunity to present the paper. If you have.
Yeah.
Can I?
Yeah.
Sir, am I audible?
Yeah, audible. Chandrakirti?
Yes, sir. You're not visible, but.
You want to see? Okay.
No, okay.
So, thanks for the talk on design of low power PLL, right?
Yes, sir.
So I have one question.
Okay.
See, for what frequency you have designed this one? For what frequency?
So the reference frequency always depends on what output frequency we want. I would say we've designed it around a few gigahertz, 1 to 2 gigahertz almost.
So for what applications you have designed this one? Like there are different applications is there, right? So
right.
For what applications you have designed this PLL?
This is a basic analog PLL itself. This could be used anywhere except for digital applications, I would say. There are digital PLLs as well for digital applications where you can have logic states and all that.
My question is, let's say, suppose if I want to design PLL for Bluetooth module, or Bluetooth,
The first
Bluetooth or Wi-Fi modules.
Wi-Fi module. Okay.
So do you know what is that frequency range and how we are going to design for this design of this PLL? Can you tell me a little bit about the design parameters? Like let's say for Wi-Fi modules or Zigbee or some Bluetooth modules. What are the important parameters we have to consider when you are going to design for PLL?
So with Wi-Fi, I would say there are different frequencies. It range about megahertz to gigahertz for Wi-Fi modules. It depends on how much area we cover. I mean how long we wanted to connect, right? So I'd say depending on the output, do I want a 80 megahertz Wi-Fi frequency or do I want a 1 gigahertz frequency? With respect to that, I would give my reference frequency.
Okay, nice. Thank you.
Okay. Good morning to everyone. Welcome to the IN Research Forum. Today, the next talk is about Debidas Kundu. He received the BTech degree from the West Bengal University of Technology, West Bengal, India in 2011, and ME degree from Bengal Engineering and Science University, Shivapur, India in 2013. He received the PhD degree from the Department of Electronics and Electrical Communication Engineer, Indian Institute of Technology, Kharagpur, India in 2018. After submitting his thesis, he was with BITS Pilani KK Birla Goa campus as a visiting faculty from January 2018 to December 2018. In 2018, Dr. Kundu received the DST Inspire Faculty Award and subsequently joined the ECE department of IIT Roorkee as an Inspired faculty in January 2019. Since April 2022 of his Inspired tenure, he is working as a visiting researcher and postdoc at Carleton University, Canada.
Thanks for the nice introduction. Can you hear me all?
Yes, sir.
I capture my video also.
Sir, you can start your presentation, sir.
Is it visible?
Please turn on your video, sir.
Just a moment. Am I audible now?
Yeah, audible, sir.
And my screen is visible?
Yeah, visible, sir. Clearly.
Okay. So thank you for the nice introduction. And thank you for inviting me to deliver a talk in your conference. I am really honored to be here and take part in this conference. Hope my talk will be interesting to the audience, and I would like to take questions from you also. But at the end of the session, maybe after my talk, we can have the discussion, and you can feel free to send your questions through chat. I think that is the procedure here also. So let me begin my talk now. So today I will be delivering my talk on design techniques and analysis of reconfigurable intelligent surfaces, also popularly known as RIS. Before going into the details of RIS and its design and analysis techniques, I want to just introduce briefly about my broad research areas. So I am currently working on surface electromagnetics. In surface electromagnetics, we actually engineer some surfaces like metallic surface or dielectric surface or metallodielectric surfaces and try to obtain some functionalities when an electromagnetic wave interacts with it. So here in figure 1, you can see there is a copper-cladded PCB. We have patterned it with some periodicity in two different cases. And you can see in figure 2 different functionalities, such as in the left-hand side, this is one polarization converter where a linearly polarized wave is incident on it, but the reflected wave is circularly polarized. Similarly, we can increase the gain of an antenna by reflecting it using a reflect array, or we can reduce the RCS of the incident electromagnetic wave by absorbing it. There are plenty of other functionalities also. So these functionalities actually can augment the existing RF and microwave circuits and system, and also can provide new applications. So my research not only on the application side, but also on the theory side. These surface electromagnetics, we can model the surfaces using equivalent surface susceptibilities or impedances and can characterize them from those properties. So surface electromagnetics, as I was talking, they have many functionalities, and you can see here there are some key applications I have provided. One is in satellite communication. We can use them as reflect array. In 5G and next generation communications, we can use them as intelligent reflective surface or reflective intelligent surfaces, on which I will discuss today. Also, it can be used for automotive radar at high frequencies and in defense radar for low RCS applications. So now, what is reconfigurable intelligent surface? So it is basically a reflecting surface or a transmitting surface also, but today's talk will be confined on reflective surface only. So in reflective surface, you can see there is a copper backplane or backplane, which will reflect the incident wave. But now the engineering will be done on the top of the PCB, where there will be array of elements. So this is single element. I think you can see my arrow. Otherwise, I want to also show the laser pointer. Here it is. Yeah. So this is a single element. So similar such elements are here to construct the array. Now this array can radiate the incident electromagnetic wave to desired directions. So to radiate them to any desired direction, we need to actually provide some phase distribution and amplitude distribution on the surface. How to do that? We can use some control circuit, and that control circuit will bias some active components or active devices such as PIN diode or varactor diode. Those active devices are connected on those elements. So by changing the biasing state, we can get different phase and amplitude value, and you will see how different phase and amplitude can actually steer the beam in any different direction. So this is the architecture of an reconfigurable intelligent surface. These are also called electronically reconfigurable metasurface reflectors. So just a minute, can I cannot see the title of my slide. Okay. Anyway, so why RIS? So you can understand that today we are living in wireless communication world. Now, like here I am in a totally different time zone in a different country, but I can talk or connect with you due to this possibility of wireless communication. So, but the problem is the demand for data rate or bandwidth and energy efficiency is ever increasing. So as it is increasing, we are now facing new challenges. Like for 2D, 2G and 3G or GSM, we use the low frequencies, and at low frequencies, there are many other applications. So those spectrums are now overcrowded. So we need to go or look for higher frequencies if we want to accommodate more user, or we want to have more energy efficient coverages and connectivity. So, but problem is if we increase the frequency, we have to also take into account the propagation loss that is mainly due to the atmospheric attenuation and diffraction, also fading effect, etc. And another main limitation is that as we increase the frequency, the wavelength will be reduced. So shorter wavelength means limited coverage. So your coverage area will be reduced. So here you can see generally the 2G or 3G base stations or access points, they use omnidirectional antennas. In omnidirectional antennas, the antenna provides the radiation to all the directions. But as we increase the frequency, the coverage is limited now. We need to use that radiated power very judiciously. That means we cannot waste the radiated power to certain direction where there is no users. Okay, we want to only direct the beam to somewhere where the users are. So to do that, we can actually increase the number of elements or antennas in the base station. So we can use the array of antenna elements. By using array of antenna elements and its phase distribution, we can have narrow beam. So we are actually directing the beam to certain particular direction by actually not directing to other direction. Power at other direction is reduced and it is directed to particular direction. So gain is enhanced. So gain enhanced means we can get longer distance. But now the coverage area is limited. So if I have one user here, then there is no problem. It can get good coverage. But if there is one user here, then it will not get any coverage. So for that, we need actually beamforming or beam steering. So this beam should be steered and at different directions so that whenever there is one user or multiple users, we can direct multiple beams or steer the beam to particular location. To do that, we have already one technology that is called phased array, but I will tell what are the limitations of phased array here. So we are now proposing or thinking that the solution might be like this. We have a simple base station, maybe single antenna element or few antenna elements, but there is one reflecting surface with multiple unit cells. So this will actually steer the beam. After getting incident wave from here, it will reflect the beam to different users. And there will be some control link from the base station and from the user also, so that the surface, which is now we are calling intelligent surface, can know the location of the user and distance from it. So For phased array, there is one problem because phased array, they have some feeding network associated with the antenna element. It is also array of antennas, but it has a feeding network. So in the feeding network, we will have phase shifter accommodated with them, some attenuator, also some power amplifiers. There are two types of phased array. One is passive phased array, another is active phased array. Active phased array, each of the antenna element will be connected to the power amplifier. So this is complicated and costly also. As compared to the phased array, here the reconfigurable intelligent surface is completely passive. It does not require any RF front-end design or these phase shifter, attenuator, and power amplifier. We will have some tunable elements. So it can actually provide us the required phase shift and also control over gain so that we can steer the beam to many directions as we want. So it has advantages. Another advantage is that with this reconfigurable intelligent surface, we are now having two paths. One is direct path and another is this path from the base station to the users. So it will give me more channel capacity. So these are the advantages of configurable intelligent surface. And as we are going for the high frequencies, in future, we will see like in 6G and beyond 6G, we will see these kind of reconfigurable intelligent surfaces are mounted or deployed on the walls of the buildings and different base stations. Only few base stations are there are sending signals, and those signals or electromagnetic waves are electronically directed to the intended user. We can get massive connectivity using MIMO techniques. We can use them, the reconfigurable intelligent surface, for larger bandwidth and a larger data rate for augmented reality or virtual reality. We can use them for physical layer security. Even in the smart office, you can think of there is one access point. From the access point, you can reflect the beam and steer them with higher power and broader bandwidth or higher data rate to the users. So this is how future might look like. So to design the reconfigurable intelligent surface, we need to understand the theory of reflect arrays. So reflect array actually comes from a very well-known antenna, that is parabolic reflector. Parabolic reflector, actually with this shape of the parabola, we can have the desired phase distribution to direct a beam with higher directivity. But the problem with parabolic reflector is that they are bulky and they have limited beam scan. And I have discussed that phased array are having higher power loss due to the feeding network. And even though they are flexible beam, but if we want to steer the beam, then they have some RF front-end design and other complications and economically also costly. So reflect array can take the advantage of microstrip array, where it is also planar and low profile, low mass, but it does not have the feeding network. It is easy to fabricate and easy to deploy as compared to the parabolic reflector, and we can scan the beam very easily. We can generate multiple beams also. Now, my research is actually on PCB-based reconfigurable intelligent surfaces or reflectors, but nowadays people are also going on chip reconfigurable intelligent surface, mainly silicon-based reconfigurable intelligent surface for terahertz communications and millimeter wave communication. But the theory and the basic design techniques are same. Anyway, so for phase distribution, you can consider that you have one access point or base station here, which we are also considering as feed. So from base station, the omnidirectional antenna is radiating, and then we are trying to reflect it to our desired users. So when we want to reflect it to any desired direction, we need to give some phase compensation on different elements on the reflector. These blue lines are the reflector elements. So this phase compensation is nothing but the difference between this path and this path to the certain direction. So after some derivation, you can find out for a beam towards any location theta 0, phi 0, what will be your required phase. on the ith element. So this equation 2 can give you. Now with that, we will have some design goals. So first I will show one reflector array design, then I will go for the reconfigurable intelligent surface, because reflector array design is the basic for the understanding of the reconfigurable intelligent surface. So the design goals are generally beam direction, of course, and you have to have very high gain, more than 20 dB. Efficiency should be high, certain bandwidth requirement, and radiation patterns, certain requirements are there. And you have some flexibility on the design parameter side. You will have the PCB with certain size, the location of the access point or the base station, its pattern, the antenna on the base station, and also which antenna element you want to choose, like patch or ring or dipole, etc., and which substrate you want to use. So those design parameters you have, you can choose that according to your requirement. So these design actually are like, you can design with using the two paths. One path is element design, another path is system design. So element design, you have to choose certain elements and you have to know its behavior with respect to its parameters. Full wave simulations are necessary, parametric studies are necessary. Then in the system design, as you know the beam direction and you have the requirement of the gain, you can calculate the efficiency, required aperture size, the location of the feed is also given to you. So you have to understand for which radiated beam, how much would be the phase compensation on the surface. So here there is a connectivity between the element design and the system design. So these elements are now will be used on the reflector array aperture, or you can say that these elements will be used to construct the array with n cross n elements, and then we can find out the far field radiation pattern by either theory or full wave simulations, etc., and we can compare them by measurement. So this is the design flow for a configurable intelligent surface as well as reflector array. So here we have designed one reflector array for CubeSat intersatellite links. So CubeSats are being thought of this global IoT-based connectivity to the LEO satellite orbit. So what will happen? You will have multiple CubeSats, small, very small size of satellites, and those satellites will provide you connectivity across the globe. But those CubeSats also require connectivity between themselves. So these reflector array can actually, the design reflector here can actually provide such connectivity between two satellites. So I will not go into the details how the design has been done, but you can see for directing the beam for a incident wave from -27 degree angle to the reflected angle 23 degree, this is the phase pattern. This is the phase pattern which looks like. Okay, so the phase can change from 0 to 360 degree, and at different element you will have different phase values. So you have to provide such phases using either passive elements or active elements. So here we are using one passive element for the reflector array, because this reflector array only steer the beam to 23 degree, does not steer digitally or electronically. So this is giving me 360 degree phase coverage. Now I can design the reflector array with certain different length distribution according to the desired phase distribution calculated here. And this phase calculation has been done from the equation 1 that I discussed already. So you can see the equation here again, equation 3. So now what I am doing, I want to choose a particular length which will give me that certain phase. So for that, a simple optimization is done. We have minimized the objective function where there is achievable phase and desired phase. The error between them two will be reduced, and we can find out the length corresponding to the minimum error. So this is the phase error distribution. Now you see the construction of the reflector array here. So reflector array is constructed here. This is my reflector array. It has 36 cross 36 elements. And there is a feeding horn here for the reflector array, and it is also measured inside anechoic chamber, and you can see the construction of the reflector array. It is in general construction using full wave simulator. You can generate the mask for the reflector array, such huge number of elements, 36 cross 36 elements. So this is, you can automate using the full wave simulators. So now I will show you the radiation patterns of it. You can see the radiation patterns. It directs the beam to 23 degree, and at the other plane it is at 0 degree. Gain is as high as 32 dBi, and aperture efficiency is also 55%. So this is the basic design techniques for reflector array, but these will be useful for designing reconfigurable intelligent surface also. So now I will discuss on how to design the reconfigurable intelligent surface, also called as reconfigurable metasurface reflectors. So till now I discussed feed with a certain source like horn antenna, but for reconfigurable intelligent surface, we can consider two types of feed. One is there is a feeding source from the base station or access point, or your incident wave is coming from some far distant away source, and you can consider them as plane wave. The wave far distant away source coming from that you can consider as plane wave. So two types of illumination you can get. So for the first kind of illumination, you have applications for base stations, ground radars, and for plane wave incidents, as well as these source incidents, you have applications for reconfigurable intelligent surface. So now to have the reconfigurability of the phase distribution so that you can steer the beam. Phase distribution is the main criteria to steer the beam. So certain beam direction requires some certain phase distribution on the surface of the array. So to have that phase distribution, reconfigurability on the phase distribution, you need to use some active components which can change the phase distribution on the surface. So we are using either PIN diodes or vector diodes, even graphenes also, which actually, if we change the biasing condition, will give you certain different electrical properties, and for that we will get different phase values. So instead of continuous phase distribution like the reflector array, you now have some discrete phase values like PIN diode. If it has one PIN diode, we can have PIN on and off. That means we can have only two different phase states. So with two different phase states, 0 degree or 180 degree, we can call that reconfigurable intelligent surface unit cell as 1-bit coding metasurface. So this is 1-bit coding metasurface with two phase states. Similarly, 2-bit will have total 4 states: on, off, on, and off. So it will give us 4 different phase values, and we can call it as 2-bit coding metasurface. So for 3-bit, it will have 8 phase states: 0, 0, 0 to 1, 1, 1, where 0, 0, 0 means all phases are 0 degree, then 45 degree, like that. So these are the discrete phases. Now, why do we need discrete phases? Because you see, on the reflector array aperture or the reconfigurable intelligent surface aperture, there will be active components, and you will have some limited number of elements. So to bias them and properly with some desired values, only like 2 phases or 4 phases, you cannot have some continuous phase values. With the active components, you have some discrete phases. So you have to discretize the phase distribution. So here we have discretized the phase distribution. So for reflector array, the phase distribution we can calculate using equation 3. But now for the reconfigurable intelligent surface, because we are using active component PIN diode with only 1 bit, like 1 PIN diode on each unit cell, so 2 phase state. So we are discretizing it phase 0, where the calculated phase does not belong to 90 to belong in between 90 to 270 degree, then we will provide it as phase 0, discretize is as phase 0. This is provided here. The blue colored part is now phase 0, and phase 180 means whenever the phase calculated value is or belongs to 90 to 270 degree, then we will discretize it with 180 degree phase, and the yellow color phase values are all 180 degree. That means by only using one PIN diode for each element, we can get a phase distribution to steer the beam to certain location. You can see here now. So to steer the beam to theta equal to 0 degree and phi equal to 135 degree, you can see the phase distribution on the aperture of the reflector array or reconfigurable intelligent surface, where the yellow is again the phase 180 degree or beat 1, and blue is phase 0 degree or beat 0. So only 1 bit coding metasurface, 2 phase states can give me a clear beam to theta equal to 15 degree and phi equal to 135 degree. Similarly, for theta equal to 15, phi equal to 180 degree, the phase distribution only change. We have to use that on corresponding to that phase distribution, the state of the PIN diode, whether it will be on and off. Like in the yellow colored portion, all the PIN diodes will be on, and blue colored portion, they will be off. So then you will get the desired beam to any desired direction in the free space. So here one bit coding unit cell is shown. This is the like basic building block for the reconfigurable intelligent surface. So as I discussed, there will be one ground or copper, conducting copper, continuous conducting copper. And now on top of that, on the other side of the PCB, you have the unit cell with the PIN diodes connected. So if you switch on and off this PIN diode, you will get two different phases. If you can consider this phase as 0 degree, then it is 180 degree different from this phase. That means it is giving me two different relative phases, 0 degree and 180 degree. And for this, I am not changing the amplitude. Amplitude should be as high as possible for this case. But if we want to control the gain or side lobe level, you can change the amplitude also. That I will show also here. So the phase distribution, we are using only 1 bit coding metasurface, that means 2 phases. So using that 2 phases, now I have designed one linear array. In this work, you can see the linear array is having all elements same phases to one particular direction, but different phases to other direction. And for this condition, with linearly polarized wave and plane wave incident, you will have a deflected 2 beams with different directions as we change the distribution of the phase on the surface. Like this distribution is changed from here to here to here. You can see the 3 different patterns: red color, blue color, and black color patterns, and they are directed to different angles. So we can steer the beam according to our phase distribution. But as we are discretizing the phase distribution, there are some disadvantage of it also. So we have to see here, you can see due to the phase quantization or discretization, when we are using 1 bit coding metasurface, then the side lobe level is increased as compared to the continuous phasing distribution. But if we use 3 bit coding metasurface, that means only 8 phase states, then it is almost same as the continuous phase distribution. So that is a good side of using the reconfigurable intelligent surface. Only 8 phase states can give you as close as the continuous phase distribution. Similarly, here the gain is a little bit reduced due to the discretization, and efficiency also a little bit reduced. But again, when you are increasing the number of bits, it is coming as close as to the continuous phase distribution. So now there is these intelligent surfaces. We can use them for different purposes, not only to generate one beam and steer that beam, we can generate multiple beams at a time from the single source. And we can provide the communication or coverage to two different users. For massive MIMO, it is very useful. So to design that multi-beam, we need to use the array theory properly. That means I have now two different directions. Means suppose I want to generate two beams at a time. That means I have two different directions. That means I need two different phase values here. And if I want to also control the side lobe levels, then I need to also control the amplitude distribution on the surface. So the required phase and amplitude should be arranged like this for beams, number of beams 1 to n, and then we can multiply that with the array factor to find out the cumulative radiation pattern. Now I am telling about controlling the phase and amplitude. Before this, I was only talking about the phase control. So to control the amplitude, what we can do, we can use director diode for phase control and PIN diode in forward bias for amplitude control. So here, director capacitance, if we change, you can see the phase is changing. And here, if we change the bias voltage of the forward bias voltage of the PIN diode, the resistance of the diode will change, and it will give you different reflection levels. So reflection levels are controlled by the PIN diode on the forward bias voltage or forward bias state, and the director can give you the phase control. Now we can calculate the radiation pattern with those amplitude and phase values with particular distribution using these formulas 7 and 8. What will be my radiation pattern? So in this case, we have only shown here the theoretical calculated result and the full wave simulated results. The measurement is still ongoing. So you see here, there is a beam towards broadside direction. Then we have steered the beam to theta equal to 30 degree. And then the same theta equal to 30 degree beam, we have reduced the side lobe levels. Side lobe levels reduction is also necessary for interference reduction, because you will have multiple beams very close to each other. So their side lobe levels as low as possible is desirable. Similarly, you can generate multiple beams. Here we have shown two beams at two different angles. So this is possible by using both amplitude and phase distribution on the intelligent surface. Another approach we are also using here, that is electromechanical reconfigurable intelligent surface. That means the elements on the surface, we can change their location electromechanically using some motors, steeper motors. We can change the position of the unit element. And if we change the position of the unit element, it will provide you different phase with respect to the source. So phase is being controlled by the height of the phasing element, and then the amplitude will be controlled by the bias, forward bias state or forward bias voltage of the PIN diode. So both amplitude and phase are controlled. Phase is being controlled electromechanically and mechanically, and this amplitude is being controlled electronically. So here again, you can see the beam theta equal to 0 degree is steered to theta equal to 30 degrees. So these are full wave simulated results, and also this case we have done the measurement in the electromechanical beam steering. The red dotted curve is the measured result, and they actually provide you good agreement also. So these works are ongoing. We have applied for some patents, and some publications are also ongoing. So now I want to conclude with this slide. That is, the future wireless communications will look like this. So for 6G and beyond 6G, we have to use some reconfigurable intelligent surface for better coverage and better bandwidth and data rates. We have to use massive MIMO, and those will be very easy by using some intelligent surfaces placed at the walls of the buildings or some different locations, and you can provide the coverage anywhere efficiently. So with this, I want to conclude my talk. So if you have any queries, please feel free to ask me. By the way, this is our group. You can visit these links to see our research activities.
So thank you, Dr. Devidas, for such an informative session. So next, the stage is open for the audience. We would love to have some questions from the audience. Any questions from the audience?
Meeting talk. I just want to ask a question. About the active phase array antenna. So
Yes.
what is the limitation of intelligent reflective surface compared to active phase array?
Can you please talk a little bit louder?
Yeah, 1 second.
Can you please ask the question again? I could not hear you properly. There was
you
echo and
Yeah, you have mentioned about the active phase antenna, like where we use different phase sources, amplifiers, and definitely it is having more flexibility compared to passive phase array antenna. So this reflective intelligence surfaces, how it is what are the limitations are there for RIS compared to active phase array antenna?
yeah, see, the techniques are similar. Here also you have some phase shifters which can give you tunable phases, and depending on the phase distribution on the aperture, you can direct a beam to certain direction. In RIS also, you will have tunable elements and you can direct the beam towards certain direction. But advantage, the RIS has different advantages. Like advantage of RISs are like this. You do not need to include the phase shifters at the backside of the phased array or at the backside of the array. So you do not need any feeding network. I think you know for the phased array, there will be a feeding network. You can launch the wave using some cable and SMA connector, and the feeding network will give you the excitation to each of the elements on the array. So this feeding network concept is not here anymore. That is why less expensive, less complex. You have a certain excitation from the outside. Source is from the outside. So like the base station or the access point is your source now. You are reflecting that incident wave from the source by using the array on that intelligent surface. The array elements are tunable now by using the active component. So it has advantages, less complex, economical, etc. And also you can see another advantage here. Phased array, you have to use at the access point itself. So phased array access point cannot give you another communication path. So you have one direct channel with the RIS and another reflect channel. But for the phased array, you will have single link between the user and the access point. So it increases the channel capacity. With the RIS, you will get more capacity as compared to phased array.
Okay, thank you, Dr. Fani.
Thank you, Dr. Guru. Thank you for your insightful talk. We will talk to you later on.
Yeah, thank you. And is there any other questions?
Okay, thank you, Dr. Devidas, for your valuable time. Thank you.
Yeah, thanks a lot for the invitation. Sorry, I wanted to complete in time. I don't know whether I concluded in time or took more time.
Okay, sir, not an issue. Okay.
Yeah, okay.
Okay, so in this Young Researcher Forum, our next speaker is Dr. Subhrajit Mukherjee.
Hi, can you hear me clearly?
Okay, sir, just a minute, sir.
Sure, no problem.
Now I request Dr. T. Sinavas to come, Professor T. Sinavas to come. We just have a good moment for you, sir.
Great. Thank you.
Okay, so in this Young Researcher Forum, our next speaker is Dr. Subhrajit Mukherjee. So his title of the talk is Optoelectronic Modulation of Ferroelectric Semiconductor Heterojunctions for Multi-bit Memory Devices. So before going to the talk, let's just introduce Dr. Subhrajit Mukherjee. Dr. Subhrajit Mukherjee currently working as a postdoctoral fellow at Israel Institute of Technology. He received his PhD degree from IIT Kharagpur. Prior, he earned MTech in Solid State Technology from IIT Kharagpur. He also received his MSc degree from IIT BHU and BSc degree from Calcutta University in the year of 2009. His research is currently involved in a wide variety of micro and nanoscale device fabrication processes using 2D ferroelectric materials for optically controlled integrated memory devices. So without a further ado, we would like to welcome Dr. Subhrajit Mukherjee.
Thank you very much for the introduction. It's my pleasure to present here. So can you confirm that the sound is clear and audible?
Yes, sir, you are audible, sir.
Okay, okay, great. So I'm sharing my screen. So today I'm going to talk about 2D material based and their heterojunction based multi-bit memory device, which is basically controlled by optical light input also, as well as the electrical input like a gate pulse or source train pulse. So my main active cells here are basically fabricated by 2D material, and we know like 2D materials family are very rich in their properties. It can be insulating like HBN, metallic like graphene, or semiconductor with different band gap lying from the ultraviolet to visible to infrared region. So if you can choose different type of material and combine them like our playing card, you can win the game. So yeah, here is my outline of my today's presentation. So I will just divided the topics in different subsections. So I will introduce with the topic a little bit and then motivation behind the work with their experimental methods and result. So in experimental part, I will using mainly two type of devices. One is the planar heterojunction, another is the vertical or van der Waals heterojunctions. So right now we are quite know about the Moore's law and the buzz about the why the Moore's law is not following like their trend line, like etc. Here in before 2005, it was a happy scaling era in terms of scalability to reduce the size of the transistors. But after that, it was quite tough. Then researchers are invented to different way to reduce the dimensions, like a FinFET structure or the gate all around structures, or even the 2D layers stacked on one upon another. So it can be a different channel on the vertical direction, but still it can be considered as a material based scaling era or the technology based scaling era. But after 2014-15, then it was very hard to reduce the nodes in further. But because of there was a electrostatic crosstalks between the devices, if you really scale down in like a 5 nanometer node technology or even further today's technologies advancing towards 2 nanometer nodes. So it was not possible with this silicon technology implemented in this way. So here are some TM structures you can see of the devices, how it looks like if you scale down really in 2 nanometer, 3 nanometer nodes. So what could be the solutions? So there are multiple approaches are going to integrate inside the devices. It calls a CMOS plus X factor, where X factor is basically the functionality. It could be photonic, it could be quantum technology or something else. So what the first approach was taken consideration was the photonic integrated circuit. In photonic integrated circuit, basically the target was to change the interconnector because we know in the back end of line of our chip, there is a lot of interconnectors. We have to fabricate multiple steps of interconnector to like connect the billions of transistors in chip. So if you can rid of these metals, there will be huge advantage. So light could be one possible way to replace this interconnector. So also there is less cross-talking between the devices possible. And the most one advantage was there in the metallic interconnectors, at the interface between the metals and the semiconductor, there could be a joule heating, which could be like if you reduce the device size really small, then the heating is really worse to destroy your devices. Like you can feel like if you have a computer or the smartphone, it is getting heated when you use it. The same concept is here. So if you use light as an interconnector, then you can reduce the joule heating. Also, light is faster than the electronic counterparts. And it's also compatible, this like a photonic integrated circuit is compatible with the CMOS technology, so it could be possible to integrate. But still, the device footprint is not going to reduce. So in terms of the device footprint, the challenge still be there. So another attempt to reduce this its device itself was the neuromorphic devices or neuromorphic computing devices. What was the neuromorphic devices? So if you see this segment, the left one segment, this is called the von Neumann architecture, where is basically your CPU unit, memory unit, and input output are physically separated. So that means you need to take the data from the input and then you perform the computation in CPU, then store the data in memory. This memory is not, I'm talking about the hard drive memory. It's just a cache memory where you store the data for a very short time, and then and you perform your task in your system. Then at the output, you read the data. But as they are physically separated, so there are a lot of data communications between all these units. So it takes a lot of time. So there is a data latency. But if you can integrate all these units in a single input, then that single input can sense the light as an input signal. It can store the memory for a short time period and also able to perform the logic steps what is required for the task. So this type of structure is called the neuromorphic architecture. It is basically a replica of our brain functionality, where in our brain we see the many things through our eye. Then we remember the things for a certain period of time. Similar like functionality can be achievable. So here are some comparison circuit. Like this is the neural counterpart from the brain, where is a two input, which is a two neuron, separate neuron, and they can communicate through synapse, and through the post neuron, signal is transformed to the next synapse. And here is the electronic counterpart of the biological synapse, which is the neuromorphic FET. Here source and drain is, and through the channel is basically the synapse, one synapse. And if you have a gate control, that can be the another synapse where the signal is coming from. It's called the pre-synapse. And also you can, if you integrate light with that, then you have a secondary synapse, which is also a pre-synapse. So using two pre-synapse, you can modulate the post-synaptic current. If you see the technological or future direction where it could be, so it is projected that by 2030 or 2035, the neuromorphic processor can be also commercially available in the market. By the way, in 2018, IBM implemented already one neuro chip, which is basically called the, I just forgot the name. So it was in 2018 invented by IBM, one neuromorphic based chip. Oh, this is the true north chip. Yes. So you can see like this is only one till now chip fabricated by industry. So there are some examples of the 2D material based heterostructure based neuromorphic devices. So one of the like requirements to characterize this neuromorphic devices is this type of characteristics. That is, when you shine with light, then you go to you achieve the photocurrent, so you go to the higher current state, but shine off the light after your performance, the current's still there, so current's not coming back your initial state. So by this way, actually you can store the charge in your device. So there are several examples using WSE2 based or MOS2 integrated with ferroelectric materials can also perform like a positive photocurrent or negative photocurrent. Also positive memory or negative memory can be possible to achieve by this way. So, but my work is integrating the 2D ferroelectric instead of 2D semiconductors. What was the purpose of that? Like if you know if you see the ferroelectric curve, so if you pulse your devices with electric field which is higher than the coercive field, then you have some polarization which remain in your system. And these polarizations have electric field. So that electric field induced your charge modulation in your FET structures. So here is an example, like if you have a left to right polarization, you have a on current, which is a positive on current. And if you have a, your polarization is directed to the left opposite direction, then you have a negative photocurrent. So by this way, you can implement different logic steps in your devices. Further, if you integrate this ferroelectric with the 2D semiconductors, like other 2D semiconductor, which is MOS2 or WSE2, then you use that TMD's channel as a channel material of your FET. Then using this ferroelectric polarization, you can actually tune the threshold voltage. So you can actually, this is like a NAND flash memory type devices where you can tune the devices, you can read and write operation can be performed. And there are a lot of AI based application is possible using these devices such showing here. So why I choose indium selenide as a 2D ferroelectric? So basically in ferroelectric material, you see the dipoles are either oriented in the planar form or the out of plane directions. But in the beauty, this is the beauty of the structures of itself of the indium selenide, where you can found the indium selenide structure. There is also in plane ferroelectricity plus out of plane ferroelectricity, and they are coupled together. So this is one advantage. Like if you can control one of the dipoles, the opposite, like a transverse direction dipoles are automatically changed or reconfigurable. So let's say you apply the bias from the gate side, you can change the dipoles along the drain source this direction. So it will be very beneficial. And it has also a multi-phase is possible, and they are different in their electrical property. Like beta phase is electrically conductive, like a conductor. Alpha phase is a conducting. Gamma phase is a semi-insulating behavior. So you can possible to get a phase change type memory. So let's jump to the device fabrication part. How we fabricate the devices. So for that, I using the mechanical exfoliated flake, and I do the PDMS based transfer. And in this PDMS structure, I use one layer of polymer, which is PPC layer, and this is a thermoplastic PPC layer. So basically a thermoplastic layer is that type of layer. When you heat it with a glass above the glass temperature of this layer, it will be softened and it can stick. But if you further increase the temperature, it can melt it and release your materials. So by this way, we just going to the bulk sample, we exfoliate from the bulk, we put it on the our stamp, fabricated stamp, and we heat it after a certain temperature to get some flake on the stamp. Then under microscope, we found out which is the right flake or right, what is the area of the flake, what is the thickness. We can, from the transparency, we can understand the flakes like this. Then we go to our setup. We have this type of chip, which is previously fabricated by the photolithography, and where depending on our desired location, we can release the flake by increasing the temperature more than 100 degrees. And there are some residuals also possible because of this PPC layer, which can be get rid of usually by chloroform. And here are some example how it looks like after transfer on your desired substrate, which is basically here is SiO2. The purple portion is SiO2 here. And the same way, we also exfoliate the monolayer and bilayer graphene for the channel material. So one of the reason to use graphene as a channel material, because it can transport the electron very fast. So whatever, when you sign with either the electrically or optically, it can transport the information from one point to another point is very fast. So it can be work as a synaptic body. So by the similar way, we exfoliate graphene, then we like for the heterostructure fabrication, first we fabricate the ferroelectric material, then come with our secondary exfoliated layer, and under microscope we can do easy transformation or easy layer stacking by this way. Then we go for the lithography steps. So this is very standard electron beam lithography step. You can get it from anywhere. Then we do the prototypes of the devices, mounting the chip on our PCB. Then by wire bonding, we have this type of structures. Then we go for the further measurement. Here is one examples of the devices, how it looks like when you do the multi-terminal heterostructure devices. This is our AFM image, and this inset is of optical image of the devices. And here is the TEM cross sections of the devices. The top one is the entire devices. You see this bright two spot as the metal, and in between your channel is lying. And in channel you have the ferroelectric slab, which is indium selenide, and here is the graphene channel. And we have the like a map also, ILS map, to distinguish what is the elemental contributions of each channel. Then the question is that how we define the ferroelectric behavior in our material. For that, because this is very small, we cannot do the P loop tracer, such kind of measurement here. So we use the KPFM style measurement. Also the PFM can be done, but we stick with the KPFM, which is Kelvin force microscopy, where we scan the potential of the devices, like map the potential. So we know the potential is basically, if you plot the potential like this is the surface potential for different gate voltage, and this is the channel. Two end is electrode, which is marked as source and drain. And from the slope, you can get the electric field by using this equation, which is electric field is minus dVdx. So from there, you can plot the in-plane ferroelectric field versus gate voltage. And you see that dipoles related to your polarity, which can sign change from positive to negative side. And if you go from that, let's say negative, from starting from 0 to positive, and then go back to the negative again, and go back to the positive again by forming a loop structure, then you see a hysteretic behavior, which is basically the ferroelectric nature of like the ferroelectric characteristics of any type of material. By this way, you can confirm the ferroelectric behavior of your material. In the next step, we also fabricate the heterostructure. This is the in-plane heterostructure. For that, what we do, we fabricate the devices on indium selenide itself. Then using the laser writing, we change the property of the half of the channel. For that case, it was indium selenide. So when you shine with high power laser at the atmospheric oxygenic environment, it would be indium oxide. And that indium oxide, like depending on many factors like laser power, exposure time, and we optimize all these things. And we saw from the top seams characterization, we see there is a anisotropic cylindrical formations happen when at the position where you shine with laser. So by this way, you can confirm, okay, there is a indium oxide formation. It is very anisotropic and directed through the laser directions. So let's come into the like the characteristics of the devices. This is just a basic indium selenide structure. So here we want to say like what happened if you shine with laser. So for the pristine devices, we see there is a Schottky type electrical characteristics, and potentials are like this way. So which is basically the semiconductor type potential map. But if you shine with light, the entire channel, first of all, the conductivity is jump of 2 order. So for the pristine, it was in this region 10 to the minus 5 Siemens per meter. But for 10 exposed, when you expose the channel, it goes to 10 to the power minus 3. So almost 2 orders of jump. Second important thing, what happened, the short barrier transformed from Schottky to ohmic. So you see there is a linear characteristic. So before it was a Schottky type characteristics or the nonlinear characteristics. Now here is a linear characteristic, which is very beneficial in terms of the device point of view. Because when you fabricate the device, our main aim to reduce the contact resistance. In next step, we go for the opto-memory characteristics or the optically induced memory characteristics. So here we see like when you shine with light and do the like a circular sweep in the ID structure, like ID characteristics, which is you see in the reverse direction, there is the memory window is enhancing when you changing the gate voltage. So that means when you changing with gate voltage, you actually the ferroelectric dipoles are more and more in favorable direction. That opens the memory window in the reverse directions. Also, we found that the photoresponsivity is really dependent on the gate bias, and it increase with the one type of polarity. And for the heterojunctions like indium selenide, indium oxide heterojunctions, we saw the responsivity is also enhanced 5 times compared to the pristine blocks. So after that, we use the same device for the logic operation. So here is the diagram of the logic operations. So here we have 2 input. One is the electric input, which can be positive or negative polarity, and we have a light input, which can be defined by on or off state. So by using this 4 combination, you can get 4 different states. Like when you sign with light, you have 1 state, and then after signing off, you have the initial state. But if you then come with the electric potential pulse, you have then after withdrawal the pulse, you are self at different level because of the ferroelectric polarity. And this for the positive negative pulse, you are here. For the positive pulse, you are here. So you can distinguish 2 type of level by electrically, and for because there is a 2 type of initial current level, but optically you also get 2 type of photocurrent level. So by this way, you can implement 2 bit of logic devices. So after that, I'm describing very briefly the vertical heterojunction, how the vertical heterojunctions behave. Here, sorry, not this one. So here, I just want to say like how the junctions of the planar heterojunctions, how they behave. Like when you have like you change the gate pulse and then withdraw. Actually, we have ferroelectricity in the indium selenide side, not indium oxide side. Also, the barriers, there are 3 type of barriers, which can be indium oxide metal, indium selenide metal, plus indium selenide oxide metal. And you see the barriers can be continuously varying depending on what type of operation you are going to do. And also with increasing the drain bias in reverse side, you see the depletion width also increasing, but forward bias, there is no change of depletion width or the barrier height. Only and the reverse bias is it's changing, which is the main reason of the photocurrent or the photodiode behaves well in the reverse bias. Only you cannot see the photocurrent of the photodiode in forward bias. So you can find by this way, actually you can implement it also the band diagram. You have a clear picture how the band diagram looks like by this measurement. Next, I'm going to the same analysis of the vertical structures. In the vertical structures, we have a graphene I already saw. And interestingly, if you come with a positive pulse, when you sign with a positive pulse, you have the graphene like that. This is the Fermi level inside the graphene. So the graphene level is top on the indium selenide Fermi level. But if you sign with a negative pulse, this is pulse, not the live gate. Okay. So after withdraw this gate, you have you end up with the potential barrier with the opposite sign. So that is the reason of why the traps are like when you sign with light, why the photocarriers are traps for a certain region. So from this measurement, you also can draw the band diagram. I'm not jumping in the detail. If you have any query, you can ask anytime. So I am just directly going to the characteristics of the device, how we characteristics the synaptic devices, which can be electrically controlled. So here we apply with a gate pulse. So it's a very short gate pulse, so less than 10 milliseconds sometimes. Or you can actually vary that. It has also impact. So for this case, we change the pulse amplitude. So you see when we coming with some pulses, this period is 100 milliseconds. You see there is a more or more charge are there, which is electrically tapped. So this is implemented by the ferroelectric gate. And for here, you see that when the gate pulse is changing from like a shorter to the longer period, you see there is a more or more carriers are traps, and you have a more or more post-synaptic current behavior. Like this can be resemble, like if you read one line in one day, after 10 days, you may forget, but if you read that line every day, that you will be remembered that, that topic after 10 days. So by this same analogy can be applied here. With higher time exposure, you can end it with a higher memory state. So it can be for if you coming with, if you increasing the post-synaptic current, it's called the potentiation. And if you decrease the current, it's a habituation or forgetting. So by this way, by varying the amplitude and the pulse width, you can change the potentiation and habituation behavior. And then coming with the optical part, when we shine with optical light, same way you can implement it the memory. For the negative pulse, we don't have memory behavior because we already saw that in the band diagram there is no structure supporting the optically energized carriers. But for the positive part, you see there is a, if you increase the pulse width, all pulse amplitude of this is the optical pulse, you can implement it more or more memory. So by this way, you also can tune the memory state by introducing the higher pulse width or the higher pulse intensity. And if you use different amount of light, different energy of light, you can have a different amount of memory state at the end. So there is also the so in conclusions, there is also the industrial outlook using this 2D material based on the neuromorphic chip. They are hoping by 2030 the neuromorphic chip can be marketized. And also there is another advancement if the neuromorphic chip holds some floating gate. So also it can be used for the non-volatile memory instead of very short time memory. So also there is some challenges using the 2D materials in the chip. First of all, the material itself a channel because you need a high area uniform film for this in CMOS processing. That is really challenging. And also there is a contact resistance with the 2D materials, which is usually large compared to the silicon or germanium or indium phosphide. And the 2D material growth, transfer, chances of defect and dislocation is really high. So thank you for your attention. I'm open for some questions.
Thank you, Dr. Subhrajit, for such a nice session. So from the audience side, any questions?
Okay, I'll have a quick question. What do you think regarding this 2D materials in any form in industry scale fabrication like what we have for CMOS and everything? So what is the current status in regarding that industry scale reliable fabrication of 2D materials?
Yes, so from the industrial prospect, there is only till now the graphene is used for their touch sensor or something flexible sensor or screen, but the other TMDs yet not developed. First challenge was their material synthesis. So for the graphene, we already have the millimeter scale or even centimeter scale graphene sheet can be uniformly grown. But in using the TMDs for the industrial scale, we need some type of technology where we can have a uniform growth without any defect or dislocation. And second thing is that with graphene, it's a single molecule, single atoms are there. But in TMDs or any other material, which is ternary, we have a multiple type of atoms. So the stoichiometry is also important. So this should be fast need to resolve for any applications in industry.
Okay, thank you. I would have definitely liked to interact more, but I think we are limited by time.
Yeah, no problem, no problem.
Definitely we can keep in touch.
Okay, bye-bye.
Okay, once again, thank you, Dr. Subhrajit.
I would like to first of all to hand over the momentum to our invited speaker, Dr. Raman from IIT.
Okay, so next our speaker is Dr. Vijay Vikas Chamua. So I would like to invite Dr. Vijay Vikas to take over the session.
Okay. Good afternoon, everyone. My name is Vijay Vikas Chamua, Today, title of my presentation is Compact Dual Band 4x4 MIMO Antenna for sub 6 GHz 5G application. Today, digital world needs high data rates, low latency, high availability, more reliability. These are the standard requirement of 5G technology. 5G can operate both lower band as well as millimeter wave, and popular sub 6 GHz 5G bands are N77, N78, and N79. MIMO is the foundation of 5G technology, which fulfill the requirement of 5G technology. MIMO consists of multiple antennas at both transmitting and receiving side, which is the key factor to achieving high data rates and high channel capacity. MIMO help to increase reliability. Figure 1 shows the schematic diagram of MIMO antenna system. In order to fulfill the increased demand of compactness in MIMO system, there is a requirement to decrease the spacing of the radiating antenna element. But when we place many antennas in a compact structure, the field from one element interact with other element. Due to this, high mutual coupling occur, and mutual coupling degrades the performance of MIMO antenna. So reducing mutual coupling and enhanced isolation are the major challenges to design a MIMO antenna. This is the design flow of my proposed antenna. First of all, we select the types of antenna and substrate material, then calculate the dimension of paths, feet, and substrate by using some mathematical approach, and then simulate further to achieve the desired goal. These are the parameters required to evaluate the performance of MIMO antenna, and here we use reflection and transmission coefficient to calculate most of the above parameter. This is the first design of my antenna. Consists of 4 radiating elements placed orthogonal to each other, and the antenna contain rectangular slit and photodisturb, and the dimension of the antenna element are shown in table 1. These are the reflection coefficient and isolation coefficient simulated, but from the graph we observe narrow bandwidth and low isolation, so further optimization is required. This is the second design of my antenna. Consists with ECE slot and defected ground structure are used to reduce the mutual coupling and enhance isolation. The dimension of the antenna element are shown in table 2. These are the reflection and isolation coefficient graph, and we obtain wider bandwidth than design 1 because of the defected ground structure, and isolation is less than 10 dB. This is the final design of my antenna, and design consists with ECE slot and defected ground structure along with parasitic element are used to reduce the mutual coupling and enhance isolation, and the dimension of the parasitic element are shown in table 3. This is the reflection and isolation coefficient. Isolation coefficient, and we observe wider bandwidth and higher isolation, and the antenna operate within the range from 1.6 GHz to 4.4 GHz and cover N77 and N78 band, 5G band, and isolation goes up to -49 dB. These are the radiation pattern and current density, and this surface current distribution is mostly limited to the antenna element where the signal has been applied, which indicate good isolation among the 4 elements. These are the envelope correlation coefficient graph and diversity gain graph, and ECC basically quantifies the performance degradation due to mutual coupling, and ECC value is less than 0.001 and diversity gain is greater than 9.9. The proposed design is fabricated on FR4 substrate of thickness 1.6 millimeter by chemical etching method and tested using VNA. The dimension of the antenna is 40 millimeter length and width. We compared a simulated result with measure result and deviation. Some deviation is observed due to the limitation of imperfect fabrication. This is the comparison table. We compare our design with some recent works. This work presents a compact 4-element sub-6 GHz MIMO antenna for 5G wireless application. Defected ground structure and parasitic element are used to reduce mutual coupling. An antenna operates within the range from 1.6 to 4.4 GHz to serve in 5G new radio sub-6 GHz and 77 and 78 band. ECC is less than 0.001 and diversity gain approaches 10 dB. Compared with some similar antennas, the antenna has low profile characteristics, useful for compact device. The proposed antenna design requires further optimization for making itself a suitable candidate for MIMO application. These are the references. Thank you.
Thank you, Vijay, for your presentation.
Thank you.
Any question?
Okay, am I audible?
Yes, sir.
Okay, so just simple question. So how did you arrive at the design? You have, it looks quite complex. So what is the rationale behind that, choosing that design? Yes, this one.
First of all, we design a 4-element MIMO antenna just using 4 radiating elements, but the isolation is very low and due to mutual coupling.
Take the question. I'm talking about, let's say you have chosen a square patch. Inside a square patch,
Yes,
you
sir.
have placed a slot. And so I saw the slot is not even at the same symmetry. So what is the rationale behind choosing such a design?
This plot modify the current distribution and which increase the isolation, basically, and reducing mutual coupling among the antenna element.
So it is trial and error.
Sorry, sir?
It is based on trial and error?
No, sir, no.
Similar. So was there any particular methodology you followed?
First of all, we if you show my design closer, then first of all we select as antenna and substrate, and then using some mathematical equation we calculate the dimension of the patch, feet, and substrate.
Design for a slot, rectangular, square patch. Okay, fine. After that slot, so what is? That's the question.
Sir, there are various methods to reduce the mutual coupling, and one of the method is deflected ground structure, parasitic element, and slot, etching slot within the radiating element.
Yeah. So
These are the basically method.
Yes. So where the slot to be placed? How do you decide?
So, sir,
where the slot to be placed? How do you decide?
From literature, some we get.
Literature is also following some rationale, no? Okay, thank you.
Thank you.
Just wait for
Okay, next presentation is by Smita De.
Hello, everyone.
Okay, we will just wait for 5 minutes. After 5 minutes, we will start the session.
Okay, thank you.
Yeah, you can share your screen and start.
Okay, sorry for the interruption. Now you can share your screen.
Okay, I'm sharing now. Good afternoon, everyone. I'm Rimita De, and I'm here to present a review paper on graphene-based electrodes for ECG signal monitoring, different fabrication methodologies and challenges, and its the future direction. So, the traditional weight electrodes that we use have several disadvantages. Like if they are used for a very long time, they can cause skin irritation, and also they. Yes, sir.
Yes, small. Can you just full screen your screen?
Okay.
No. Yeah, now it is correct.
Okay. Yeah, the traditional ECG weight electrodes that are mostly used in day-to-day life, these causes skin irritation if they're used for a very long time. So researchers are trying to find out a type of electrodes that is flexible, wearable, and highly conductive, and at the same time lightweight. So these sensors are mainly used to find out several cardiovascular diseases. Almost 20 million people died each year in the whole world due to cardiovascular disease. So it is very important to, this field of research should get more importance than it's used to get previously. So as a ECG sensor, graphene is mostly used in case of wearable dry electrodes since it has various unique physical and chemical properties. So in this paper, we have focused on the several methodologies in which the ECG electrodes can be fabricated, and we have also talked about the advantages and disadvantages of methodologies and other parameters also. So here we will discuss about the various characteristics that graphene uniquely possesses. So the first methodology is carbon. It's a allotropy of carbon, and it is a planar hexagonal honeycomb-like structure and having some unique chemical and physical properties. It shows high electron mobility, high thermal conductivity, and also a very good mobility at high room temperature. And it is also considered to be the strongest materials tested since ever, having Young's modulus of 1 TPa. So there are various applications of graphene, they are used on solar cells, hydrogen storage, then supercapacitors, electrons, etc. And these are also used for wearable sensors. So the first method we'll talk about is screen printing. So following this printing method, various researchers have published their papers, and I have found almost more than 5 to 7 papers only following this methodology. So what happens in screen printing is the ink or the graphene ink is first prepared, and it is poured on top of a impression which needs to be printed, and the whole setup is fixed on a substrate over which the impression is created. And there are few only over on the top of the impression the ink can flow through, and in other parts it gets obstructed. So that's how the impression is made on the top of the substrate, and the ink film is made, and which acts as a electrode. And following these methods, these are the previous work which were done, like we can see, and the skin content impedance or the SNR value of the ECG signal acquired from these electrodes were almost compared to the wet electrodes. So we can see that these type of dry electrodes can replace wet electrodes, and hence we can reduce the usage of wet electrodes. So like in this case, they have found that there are almost 99.47% similarity between the ECG signal obtained from the AGAGC electrode, which is a wet commercial electrode, and between the this type of electrode, which was fabricated by screen printing method. And here are some other papers that I have found, that it shows that after one printing process, the sheet resistance could be higher, but after several printing processes, it gets decreased, and it almost it can be also compared to the commercial values. So the next process is the dip coating method. It is the most cost-effective method and is one of the earliest wet chemical thin film deposition methods. So this is a very basic method, and in this method, at a uniform speed, the substrate is immersed into the precursor solution. So in the precursor solution, the ink is already made and it is dissolved in the solution, and then the substrate is taken out of the solution at a uniform speed. And after taking it out of the solution, it is dried at a temperature or maybe at room temperature. Then after drying, we can use it as electrodes. And if we repeat this process, a sheet resistance can be decreased, and we can see better quality of ECG signal. So these are the papers that I found here, and many researchers saying that there is almost 97% precision in the ECG signal acquired from the AGAGC electrode and from this type of dip coated electrodes. So as a dip coating ink, we can use reduced graphene oxide, or many of them have used graphene and PDMS coated textile electrode, and others also. So, and we can see here that in this frequency range, the impedance value were found to be 87.5 kilo ohm to 55 kilo ohm, and in case of AGAGC electrode in the same frequency range, the value was from 50.9 kilo ohm to 20 kilo ohm. So we can see that this can the values are almost similar to the values which can be obtained from the wet electrodes. So the next method is a wet transfer method, and this method is a bit different because it is one of the costliest method, since the graphene grown is by CVD method, which is a chemical vapor deposition method, and in this way, high quality graphene can be grown on a large area. Graphene can be grown on the top of copper or nickel, and later they are transformed to the desirable substrate by wet transfer method, and that is how the electrode is fabricated. And in this method also, after PMMA is used as a supporting layer or sacrificial layer, which protects the graphene layer, since during this process the graphene layer could be the graphene layer could be gets repelled, or so that to protect the graphene layer, PMMA is used, which is later removed. So these are the previous research which has been done in this method, and this is also a highly effective method, and we can produce high quality dry electrodes from following this method. So the next method is the wet transfer and dry patterning method. So in the previous method, we saw that transferring the graphene layer from the copper substrate to the desirable substrate, an electrode is made. But in this method, one more step is added. That is after transferring the graphene layer from the copper substrate to the desirable from copper to desirable substrate, a programmable cutting plotter is used, using which we can make specific designs on over the graphene layer, and this is how the electrodes are made. and mostly the tattoo sensors, which tattoo electrodes, which are used as ECG sensors, are fabricated following this process, and which got huge attention by the researchers. So as I was talking about, the graphene electronics tattoos were made by this type of electrodes, and which was quite interesting, and the SNR value of the ECG signal following this method was 15.22 dB, as we can see here, and from the conventional method it was found to be 11 dB. So we can say that it was almost similar to the value of the ECG cell electrodes. So the next method is a spray coating method, and in this method, the electrode is this is a surface. The surface is first made, on top of which the graphene layer needs to be deposited, and this is a spray. Inside this spray, inside this volume, the graphene ink is put, and it is and when the volume of inside the space is reduced, the ink comes out in the liquid form as spray, and it gets deposited on the substrate. And after, if we dry the substrate, then we can find out then we can get the ECG electrode.
Yes, Miss Rimita.
Yes, sir.
Actually, we are going ahead of time, so can you please just brief your talk within 2 minutes?
Okay. I'll try to go fast. So this is spin coating method. One of the main advantages of this method is we can form a uniform layer of graphene on the top of a substrate following this method, which is a very good criteria. And there are not many papers I found who follow the spin coating method, but I am sure there's still in the future there will be a lot of research in this area. In the drop casting method, which is one of the most cost-effective method, is where manually or in other methods, the ink is casted on the top of the substrate, and then after that it is dried, and that is how the electrode is made. So these are the previous work which was done on the drop casting method, and most of the researchers has been done on this method only. And this is an inkjet printing and electrode spinning method. So in the inkjet printing method, the ink is first deposited, the ink is first stored in this channel, and when voltage is applied, it comes out of the nozzle in the form of aerosol, and then it gets deposited on the substrate, and the substrate keeps moving, and that's how the deposition is formed. And this method is very effective and useful. And in the electrode spinning method, we can see continuous nanofiber-like structures, and so these graphene fibers, along with other substances, can be deposited on the collector, and that is how the electrode is made. So in the vacuum filtration method, at first the ink is prepared, and it is poured on top of the nylon membrane. And if we put it in the put the nylon membrane in the hot plate, then it dry it, then we can get this type of electrode, dry electrodes, which is also a uniform process. So in the conclusion, we can say that the dip coating and drop casting method were the two most facile and subtle techniques for fabricating graphene-based electrodes, since they require very few apparatus, and which are very cheap. So these are the mostly the ideal fabrication processes, and the data that which were obtained from following these processes were almost similar to the data that we obtained from the wet electrodes. And these are the references. So this is my presentation. Thank you, everyone.
Okay, thank you, Ms. Rimita Dev, for such a nice presentation. Now, any questions from the audience or expertise?
Okay, so I'll have a quick question. Anyway, first of all, congratulations on a very elaborate talk. Just quite curious about how a graphene layer will have quality in terms of mechanical stability and electrical properties. So I guess it will be much weaker because it is amorphous in nature. So electrical conductivity will not be that good as conventional metal electrodes. If I am not correct, if I am correct.
Yes, sir. Yes, sir.
And what about the mechanical stability? Because it's a graphene layer, any scratch it will tend to damage.
Sir, for that, we use not only the graphene layer, but a different layer is also used. So in most of the cases, people mainly use PDMS layer. So actually what happens that on the
is not a conducting layer, so it will further degrades the graphene's conductivity.
Yes, sir. If then silver nanowire is the best option to go for, because silver nanowire and if a mixture of silver nanowire and graphene is mixed together, then it improves the conductivity of the electrode.
So silver nanowire and graphene has similar lattice constants. Anyway, graphene doesn't have a lattice constant. Graphene is anyway amorphous. So how are you going to tackle that?
Yes, sir. I think that it needs to be more researched, and
yeah. So that definitely, thank you. Then it should be an open area for exploration. So how to improve the conductivity and the mechanism. And thank you.
Sir, I want to say one thing, that the tattoo sensors that are used mostly, they are washable. So if someone wants to, if someone puts it on their skin, and it can be removed after it can be removed easily. So in that way, it's also advantageous, like that graphene properties.
No, I'm saying about the if you scratch graphene, graphene will come out.
Yes, sir.
If you have a good binder, if you using a good binder, then definitely the problem will be your electrical properties will go down.
Yes, sir.
Okay. Thank you.
Thank you, sir. Thank you, sir.
Okay, thank you. So now we will wind up the session. So thank you all for joining this session. Thank you.
So this topic that we have chosen for this talk is called the quantum information technology using photonics. Photonics will come as we go along, and I know some of you are in that biomedical applications. Is it not? Some of the papers are in biomedical. I hope, but this will also be of interest to you. And only a few of you are there. I suppose you are all from SRM. I think the participants are from outside, or how is that? I don't know the remaining two participants. Okay. Yes. Yeah. Anyway, welcome to my talk. Let us get started. This topic is called the quantum information technology using photonics. And you can say, you can include in general a lot of things into this, like quantum communications, quantum computing, etc. Okay, let us get going, and we'll have some discussion towards the end. So this is a brief outline of the presentation. We'll start with a brief introduction of what is quantum, a brief history of quantum information. I have named it as quantum information technology so that it can include many things, like in comparison with ICT. Many of us are familiar with ICT, information and communication technology. So you can say that quantum information technology is analogous to classical information and communication technology. Then we'll look at a little bit of history. Then we'll understand what are meant by qubits. Then I'll show you a few operations on quantum bits. Then we'll see the general structure of quantum computers, quantum communications. And then I'll go into a little bit of photonic devices implementation of this. That's the main purpose of this talk. We'll have to spend less time on the initial things and then go to photonic devices. And of course, as I have seen from your theme of the conference also, it is on photonic and electronic integrated circuits. That's the main plan for today. I suppose you already had some quantum information related lectures. Some of you, did you already attend quantum related talks, is it not, in this conference? So I think I need not spend too much time on the quantum side. We'll spend some time on the implementation side. I foresee that that is an important problem. See why we don't have a quantum computer till now, even though a lot of theories are there, so many papers are coming. One of the main reasons is we don't know how to implement. If you look at the literature, a lot of implementations are based on atomic systems, cold atoms, nuclear magnetic resonance, then squids, and so on and so forth. So these are all not suitable. If you compare this technology with VLSI technology, it is a lot of difference there. So for example, all our gadgets now, the laptops, cell phones, TV, all have got electronic devices, electronic chips inside that. They are based on VLSI. But if you want to bring in similar change, it's not possible with quantum. That is mainly because you don't have proper technology to implement all this. People foresee that photonics is a technology which will be useful for quantum applications. Not only quantum, classical applications also, photonics is a technology. But it will play a more important role. It's the only way, you can say sometimes, to implement quantum information functions. So your laptop or cell phone or the futuristic of 10 years or so will most likely contain quantum chip based on photons. That is the idea. And this is perception from the current going on, what is happening. That's what we can foresee in the future. So one of the important indicators is in the area of communications. Communications, we know all the electronics is replaced by fiber optics now. So now we have all the broadband and all these applications mainly because of fiber optic communications, not copper communications, not even due to satellites, and not even due to the mobile. See, the last mobile, the mobile phone that we are using, all the communication and data applications. But the backbone is fiber optic. The backbone is not strong. If you don't have enough bandwidth on the backbone, we don't have all these technologies right now. So fiber optics is playing an important role. Similarly, for quantum information and communication also, we need good technologies for photonics. I hope it will be. And presently existing technologies are not sufficient based on silicon. All VLSI is based on silicon and it's not sufficient. Most likely we may have to have active materials like gallium arsenide, indium phosphide based photonic ICs. That's a brief introduction to this thing. So the keyword in this is called the quantum. This today's talk, etc. And I hope you must have. I think many of the presenters earlier would have talked about a lot of algorithms. I'm just forcing. I'm just throwing some light on what the viewers may have to know. In the literature, there a lot of information is there about quantum, particularly on the algorithms and many important algorithms like search algorithms, computation, and so on and so forth are available. Implementation issues, they simply assume it can be implemented by some optical means. They will assume optical devices on a table, like in a classical physics lab table. They will assume some interferometer or whatever complex optical system can be constructed, which can implement these functions. That's what is the current picture. Not a miniature chip. Okay? But they will prove that this can be done. I'll do some examples as we go along. But the keyword here is the quantum. So quantum implies that we are using the quantum states of the objects. Let me elaborate in a minute. See, we have to distinguish between the classical phenomena and quantum phenomena. Is it muted or it's going on? In the beginning, I asked that people have listened. That's what I feel. No, I will use the arrow. Yeah. So there are classical phenomena and quantum phenomena. When someone, if you are studying physics in the college, you must have come across classical phenomena and quantum phenomena. And quantum phenomena appear when you go to atomic level. Atoms, molecules, and many of the phenomena that we understand now, the colors of the objects, and so on and so forth, can be traced to quantum phenomena, where you have the energy levels of the objects. And the transitions between the energy levels are governed by the quantum phenomena. Basically, you have to solve the Schrodinger quantum mechanics, Schrodinger's equation, and obtain the wave function, and that will define all the properties. That's what is the picture of quantum that we have from the college studies in physics. But that is not complete.
I would say that all the phenomena in the world are phenomena, and quantum nature is already there everywhere. Unless we go to quantum principles, we cannot understand many phenomena that we see today, like the colors of the objects, or even the bigger non-atomic big phenomena also will need quantum principles to understand. Maybe I will not elaborate too much because that will go into quantum mechanics and all that. So a quantum computer will work on the quantum principles. We know about the computer. It has to do a lot of computations, like solving some big problems, some big data problems, then mathematical problems, and all it has to solve. It has to do a lot of processing. So all this is being done by using electronic principles right now. And if you use quantum principles to do these operations, then you can call it as a quantum computer. These are conventional. Even the next slide, once again, I'll elaborate more about the quantum and classical. Similarly, if you are trying to send information across objects by using quantum principles, then you can call it as a quantum communication system. So this is the main crux of the problem. We should understand what is meant by classical object or classical computer, quantum computer, the classical communication system, and quantum communication system. Historically, it is attributed to Richard Feynman, who said that you can have the computation based on the quantum phenomena. By 60s or so, it is well established. The quantum principles have been well established, and then people were working about what are the limits of. See, already by that time, the transistor was invented, and people have foreseen what can happen to the electronics. But people also know that there are quantum principles involved in the transistor and all the electronic devices also. And people look at, and Richard Feynman has said that we can use quantum principles of quantum mechanics and quantum physics for computing and all these applications. Computing also was there. The basic elements of the normal conventional computer was also ready at that time. By then, people have known. But if you apply quantum principles, something totally different will be possible, and many things are possible. That's what people have foreseen. And Richard Feynman is the one who has one of the first persons who has announced or declared that quantum principles can be used. So this is a brief timeline of the development of quantum information theory. Starting with the Feynman's idea, then first protocol. If you want to, I think I should elaborate as we go along. If you want to use quantum principles for communication, you cannot just like that do like the classical sending the signals across points. So we have to define how do you incorporate this quantum information into the carrier waves. How do these channels deal with that? All those things we have to understand if you want to do the quantum communication. So some protocol is needed. You can just think about the conventional protocols that we know for the telephony, mobiles, and so on. You have a protocol. You have to lift the phone, you have to press something, numbers, some header information there, destination, and so on and so forth. That is the protocol. So in case of quantum, we are not talking about that all that protocol, but we want to understand how this quantum information is embedded into the carrier. That is what is meant by protocols. So then another example, quantum computing is similar to quantum communication computing model. Then you have what is called the idea of entanglement. This is completely new in quantum, that you can have objects which are correlated. That's an important principle. I'll describe later on. Then some people have developed a lot of other algorithms like Peter Shor's algorithm for searching big database, Grover's algorithm. Then people have built models of computers, quantum computers. Then coming back to the more recent times, we have the Chinese have developed this long distance telecom link, 2000 kilometers quantum communication link. They have demonstrated in 2016, called the Mencius 1. So they have transmitted quantum information over 200 kilometers. Similarly, intercontinental voice and video data has been transmitted. And now you can foresee that a lot of companies are jumping into this bad weather. Indian government also has realized that we have to work on quantum. And many universities also are taking up the programs on quantum communication, quantum computing, and quantum information. And so many companies. This is an example. like Google has announced 72 qubit quantum system. These are all the recent developments. So now the last 10 years or 5 years, there's a lot of interest and hype in quantum information, particularly for those academic people. Particularly, there's a lot of scope for taking up these projects and doing research and all that. That is the scope for the quantum information technology. And people have to understand the real world situation and what is possible, what is not possible, how to implement. That is the key to the future, we can say. Not simply development of algorithms, mathematics, and so on. That is needed, definitely, yes. But people have to understand how to implement, how to make use of it, what is the problem we have to solve, and all. That's where we have to focus when someone wants to do research or develop some projects. So to start with, we'll understand what is meant by a qubit. So in classical information theory, we have bits represented by zeros and ones, and which are physically represented by using the currents and voltages. You can say that high voltage across a circuit is a bit 1 and low voltage is bit 0. That is the ideal picture. Or current or light. Nowadays we use optical communication. You can use horizontal polarization for a 0 bit and vertical polarization for 1 bit. So that is a picture of a classical information bit. In contrast to that, when you want to define the qubit, you have to define with respect to the quantum properties. We have just now mentioned in the beginning that you have to go to atomic level or small objects if you want to observe the quantum phenomena. Even though that's not complete picture, let us assume, let's start with the classical definition. If you have a photon, for example, I'll just for that in this lecture, we'll take photons as the example, not electrons or atomic systems, because it's an optical related lecture. So if you take a photon, for example, it's a quantum object, it is governed by all the quantum principles. It cannot be destroyed, it cannot be separately created, it has got an energy levels, it has got a momentum, it has got a polarization, all these properties are there for the photon. But the most important property that we have to understand is all these properties are not deterministic. We have to compare with the light wave. If you have a light wave, we can say this is the polarization, this is the mode, this is the direction of propagation, this is the energy, and so on and so forth. For a light wave. For a photon, we cannot say that. We can only say that the polarization is horizontal with so much probability. The polarization is vertical with so much probability. The only probability we can mention. That means the photon can be in any polarization. Any polarization. We cannot exactly specify. We cannot measure. Once you measure, it will be that suppose you measure horizontal polarization, it will show horizontal polarization, but with that probability. So probability is an important concept related to the quantum states. And as I mentioned earlier, you have to solve the quantum mechanics, the Schrodinger equation, and get these probabilities. In particular, if you are in the ECE communication subject, you know we define with the PDFs, probability distribution functions, probability distribution functions and distribution functions. If something is not definite, we can define by the PDF. Horizontal polarization has a PDF. In this direction, it's such probability, and all that is. Similarly, vertical polarization, that's probability. So we are dealing with the PDFs, and so we use the ket notation, 0 ket and 1 ket to represent the qubits. 0 qubit and 1 qubit. 0 ket and 1 ket are the averages of this. The PDF distribution has got the mean. So that is what is 0 ket and 1 ket. And a superposition of these 0 ket and 1 ket is the state of the photon. What is the interpretation of this wave? This is called the wave function. And the interpretation of this wave function is the square of that will give the actual probability. The PDF, the wave function, the square of that is the actual PDF, not the function itself. So we have alpha square plus beta square, which are the probabilities. The square should be totally equal to 1. Probability of getting 0 is alpha square, probability of getting 1 is 1. You can also put it in polar coordinates. Instead of rectangular coordinates, you can put in polar coordinates. And you can, if you have from the linear algebra, we can see that psi is represented by a linear combination of the horizontal and vertical state, or 0 and 1 ket. And you can also represent 0 and 1 ket by some matrices. If you are looking at input output configurations, so 0 ket can be represented by one matrix 0, 1. One ket can be represented by 1, 0, another matrix, and a linear combination will be a 2 by 2 matrix for this 1 qubit system. 1 qubit, we are talking about 1 qubit. Someone can ask me a question between also. If online people want to ask a question, they can put it in the chat box and organizers can forward it to me. So you can also represent pictorially the idea of this qubit. So you can see from this equation that psi is a linear combination of alpha and beta. Alpha and beta can take all values, including imaginary values. As you know, in the wave function, it's a complex function, not only real function. The square of that is giving the probability. So alpha and you are in the complex domain, in the linear algebra with complex coefficients and so on. So all the points on this sphere will represent the states of the object. So there are infinite states for the objects, which can be used to represent the qubit values. And the 0 ket and 1 ket or can be set with the basis of this vector space. And this psi will span the entire, the 0 and ket will span the entire space of the vector space of psi. And this is called the broad sphere. This is for 1 qubit system, you can say. You can talk about multiple qubits. We are not talking about only 1 qubit. In any communication or in information technology, we use many qubits. That means you have to have many objects. Suppose 2 photons. You have a 2 qubit system. Each photon can be its own independent qubit state, and the combination of that is going to give you many 2 qubit system. Or similarly, multiple qubits. If there are n photons, you can have n qubit system. So they are not correlated. The photons are independent. That's what I'm considering now. Later on, we'll talk about entangled photons where there's correlation with photons. If they are independent, you have 4 possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. And the composite system can be said to be a linear combination of the 4 basis states. They are represented by 0, 0, 0, 1, 1, 0, and 1, 1. You can also represent by x1, x2, x3, x4 as the basis. And this is a linear combination. Each one of them is a probability, and the square of all these alphas will be equal to 1. 4 basis system. There is no physical representation for 4-dimensional space. So now let us jump to gates. You can do a lot of operations on the qubits. You can pass these qubits through some devices like a beam splitter or a coupler. We'll talk about integrated, because this conference is also on integrated photonics. You can have an optical waveguide coupler, and then you can pass the light through that. This photon, not exactly light, the photon through that, and see what happens at the output. So input is a single photon, output is 2 outputs are there. You don't know whether the photon will come out of the first branch or second branch. But you can say that the linear combination of these 2 output states will represent the photon states and all the probabilities. That's a very good illustration of this. Like a beam splitter, we have to take parallel. If you want to understand integrated optical devices, you take the parallel with the conventional devices. Conventionally, you have a beam splitter, power divider. In integrated optics, you have a Y branch. So if you pass light through this Y branch, conventional Y branch, conventional beam splitter, light will be divided into 2 parts. If you want to send 1 milliwatt of power, half milliwatt in the first port, half milliwatt in the other side, other direction. And of course, you can have polarizing beam splitter. One polarization in one direction, other polarization in other direction, etc. The same thing, if you translate into single photon case and into integrated optics, you send 1 photon through the input, and the photon can come out of the first port or second port with some probability. You can expect half the probability if they are identical. So the output state can be represented by a linear combination, like what we said earlier. But how do you represent mathematically? Mathematically, we can represent by using these matrices. We are talking about a single qubit system. This is called a single qubit gate. One photon is given, 1 qubit is given, 1 qubit is coming out. You know, in conventional electronics also, we have single bit systems like NOT gate and so on. AND gate and all are 2-bit systems. You can have a NOT gate, for example. But there are a lot of other combinations. In the quantum case, you have a lot of other. Poly gate is like a NOT gate, and these coefficients I am showing you, so they can be imaginary also. You consider this Hadamard gate. Just now the example of Y branch I am giving. So Hadamard gate at the output has 2 possibilities, 0 and 1 ket. And the Hadamard gate output can be represented as a linear combination of 0 and 1 or 0 minus 1. So the matrix representation for the Harvard gate is this. I'll show you the physical picture in the next slide also. So there are other gates which are important. You can work out based on the input-output configurations. This is called a C0 gate. You know about the NOT gate. So if 0 qubit is given, 1 qubit comes out, and 1 qubit is if you input 1 qubit, 0 qubit comes out. But the operation of this gate can be controlled by this C port. If the C is 0 qubit, then it will act as a NOT gate. If C is a 1 qubit, it can pass through. So it's called a C0 gate. Similarly, you can have two gates, two control ports, C1 and C2, and the T is the signal. So you can work out that the matrix representation is like this: 4 by 4. Here 2 qubits, 2 qubit states for the C, 2 qubit states for the 4, and 4 input and 4 output. Similarly, if you have this 8 input and 8 output, double C0 gate. So this is how you are representing. You can represent the quantum circuits. So this is a set of criteria that have been declared for a typical quantum information system. So we have talked about the qubits. What are the properties that they should have? We have observed that we cannot determine them exactly, but we can deal with many qubits. And there are some problems also in all these things we will highlight. So the physical system should be scalable. We should have a many qubit system. We should be able to handle so many qubits. If they combine or if they decay, it's a problem. This is called the decoherence. The qubit state or the quantum state will decay with the time. It will not remain in the same state. So that's called the decoherence. Both with time, with respect to distance, with respect to other impairments, the quantum state can change. So we want to have a system or a qubit or an object whose qubit state is stable for some time, up to whatever amount of time. That's called the coherence times are important. Then we should be able to prepare the qubits by passing the qubits through certain systems like the Y branch or a beam splitter, etc. We can say this is in this likely in this state. In the beginning, it's arbitrary, nothing is known. If you pass it through a beam splitter or a Y branch, you know that this is in this state, this is in this state. Likely, we can say that. Then we need to have, like in a conventional system, we should have a universal set of gates like NOT gates, etc. We should find out, someone has to build. Already they are there in the literature. Then we should be able to move these qubits for quantum communication applications. We have to move them from one point to the other. Until now, I didn't say whether they are moving or not. If they move, their properties can change. We should be able to move these. These are called the flying qubits, moving qubits, and so on. So many other properties. So someone interested can see this paper. So this is a brief block diagram of a quantum computer. Yes.
So if you design something with that, can we the accuracy of that device will be questionable?
Yes. Actually, it is not exactly accuracy is an important problem, but how to handle is an important question. See, it is not deterministic. If you say add two numbers, then you know, so this number can come. Just as an example, suppose you are passing some information through a quantum computer. Let us say there are two processors. Just for an example, suppose there are two processors. Some input is given. So this input has to pass through both these processors. So what is it? The idea there? The information can pass through the first processor or second processor, not both. You cannot divide. You cannot copy quantum information and send this thing to this and this thing to this and then combine and all that. So what happens here? The information will pass through all the processors with a certain probability. Output also comes with a certain probability. So the output is not definite, but people have worked out by a sequence of processes, etc. You are likely to get so and so in this port, so and so in this output port, so and so in this output port. We can come to a conclusion based on this processing that this particular quantum computation has been done by this system. It's not definite. You have to have a protocol or a mechanism where you have to identify in this port, if you measure the probability of so much, in this measure so much probability, so much, all these alphas, alpha, betas, etc. You can do some observation, not exactly conventional computing, saying that this is the outcome. So the outcome of this quantum computation is defined in terms of certain everything in terms of probabilities. So that's what we should see. Suppose you are just let one more example. Suppose you are trying to search for some data. Suppose you have a sequence of 10 data functions, 10 inputs given to you. You have to find out whether a particular number is there in the input or not. Now, let us assume these are quantum objects. This data is quantum objects. X1, X2 up to Xn are quantum objects. Conventionally, if X1, X2, X3 are deterministic objects, and if Y1 is the observation that you are trying to find whether it is there in the list, you can do the classical comparison and say this is there or this is not there. Now we think of the same thing in the quantum domain. X1, X2, X3, X4, etc. are all quantum informations, which are not given definitely. There is a PDF for each of these. And also you are trying to find out some information Y, which is also a quantum information. You want to cross-check whether this Y corresponds to any of these. It will not match with any of them because it's all probable. It's only a linear combination of X1, X2, X3, etc. is what is known. And Y is also a problem. You should have an algorithm to say that if this is the outcome, this Y is matching. So what happens when you pass all this through the quantum computing system? Everything will have to happen parallelly. We are not first sending X1, next X2, etc. In the classical sense, we do that. Compare Y with X1. Not there. Throw it. X2. No. Y, no. So now we have to do simultaneously, you have to compare with all of them. So you are doing a parallel computing. Outcome is also not single entity, but several entities with different problems. Suppose, let me say there are n output ports giving n PDFs, but a combination, some what is that called, some Y1, Y2, not Y1, let me say Z1, Z2, Z3, etc. So based on the Z1 to Z10 or whatever number, based on this pattern, you can say that Y is there in this format. All the points you are doing in a parallel fashion. That is the advantage. And you don't require that sequential operation which I described in the beginning. It's not there here. And this is an advantage in the big data problems. A large amount of information, everything is mixed up. Everything is mixed up and you get an output at once in one clock cycle. I mean, very crudely, I think I have explained that way. So let us look at some typical configurations of quantum computers. You have starting with the mathematical models are already there. Then you have to have a formulation algorithm, and a lot of tools are there nowadays. All the theory that is available is programmed into classical computers. See, there is what is called the semi-classical approach to solving all these problems. Even though it's not really quantum, you can do parallel processing and say this is how it can happen. So this is called something semi-classical, using classical computers to do some quantum operations by algorithmic way. See, I think there are many of you know about the IBM's QScript and some of these tools available. So they do all these things. And it's also possible that they have, if and when the quantum computer is available, all these algorithms can run on that directly instead of simulating. So these are all called simulators. Quantum simulators are available. People can, those who want to work with the subject can register on that, you can download and then do all the algorithms can develop. And in fact, mathematically, we can come to some good conclusions that this is doing quantum computing. So these are all the typical models. Then you have the physical level, like in the OSA model, but the quantum architectures also they divide into several layers. One is the algorithmic layer, one is the device layer, and so on and so forth. So I'll not spend too much time because already I have spent. We'll go to implementation using photonics. That is the main idea in this. So we'll try to go forward. So these are different levels of people have divided for the ease of design and implementation and all that. So when it comes to quantum communication, the most important thing that I mentioned was we must be able to move the qubits from one point to the other. So there are a lot of interesting things. One of the most important ones that has attracted attention recently is called the QKD, quantum key distribution. If you are using quantum communication, you can, I'm telling you the conclusion that it can be perfectly secure. You cannot interpret or you cannot crack or you cannot steal the information. That is because information is not deterministically given across any of these ports. Suppose the transmitter and receiver are there, they have information, is not deterministic. So someone cannot steal. And there are algorithms. If someone interprets in between, it can be easily known. So people say that if you can is the most perfect system, and a lot of algorithms are there now. I will illustrate one example. So there are a lot of, like in the beginning, I mentioned that there can be different ways of representing all this quantum noise. Another important phenomena, which is also quantized, not only randomized. Random and randomization, quantization, two different aspects. We should understand with respect to information. I think I have not indicated that in the beginning. Information, when you say, it's a random process, like the coin tossing, whether head or tail, you don't know. That's a classical information. Classical information. If you have a coin tossed and close it, you don't know whether it's head or tail. That is, it has got information. Okay. Now, what is the quantum analog of that? Let us assume I have a quantum coin, let me call it. Toss it. I will not hold also. It is there like the conventional coin in the space. You don't know whether it is head or tail. You cannot know also. That is the quantum part. You cannot know. Even if you open, you cannot say whether it is head or tail. I mean, you can, by observing, you can say. As it is, you cannot say. When you observe it, it collapses to the 0 state or 1 state with the problem. Whereas in the conventional coin, definitely whether it is 0 or 1, head or tail is well observed. Okay, that is the difference. So let us go further. So this example. Now I want to just briefly mention about the entanglement. If there are two objects, you can create an entangled object by generating photons itself. You can generate entangled photons. Physical mechanism I'm not describing right now. The property is, if they are entangled, if you know the property of one object, you can predict the property of the other object. If you say suppose if they are exactly same, like it is like a coins. Suppose you have to take two coins and they are tied with some stick. So if one coin gets head, other is also head or tail. So you can say they are entangled. So if you know one property of one object, you know the property of other object. Both you need not measure at the same time. So using entanglement, very well used in quantum communications, and it is an important principle. So like photon sources, we have to, single photon sources are needed, is it not, for quantum? Similarly, you have single entangled photon sources and so on to operate. So a lot of algorithms will be based on entanglements. So, and also all these quantum states, two states, say this is a two-state system. So you have all these two states, but all states are not permitted because they are entangled. So there are 4 states are shown here. So I'll just show you one protocol for illustration. Quantum QKD protocol. And this high dimensional QKD implies you are not working only with 0 and 1, only 2 states. You can have many states. We saw that the qubit states can be many. The Bloch sphere, when you have seen, there are infinite number of states, and then 2 basis states are shown there. You can have systems with more than 2 basis states. Like earlier we have said about alpha 1, alpha 2, alpha 3, and alpha 4. So that is 4. That is Q2 qubit system. Similarly, you can have higher dimensional system where the bases are D1, D2, D3, D4, and with a linear combination of that will give you the. This is called higher dimensional system. This is one of the subjects that we are working in our department. And people also have device what is called the device independent key distribution. Theoretically, people have said that it doesn't depend on which device, whether you are using photons or electrons or polarization and so on. So they have developed the protocols and the systems which are not dependent on any device. Okay, this is just a brief description of the protocol. So there is Alice and Bob. These are the transmitter and receiver. Alice is a transmitter, Bob is a receiver, and I'm using the photons, horizontally polarized photons for 0 qubit, vertically polarized photons for 1 qubit, and also equivalently left polarized photons for 0 qubit and light polar. I can use either this or this system. You can think of them as boxes. 2 machines are there. One machine horizontal vertical and one machine left and right. So If I have a qubit to transmit, I can use the first machine or second machine to transmit. And the same object, same photon, linear combination of these two states or linear combination of these two states. Similarly, Bob also will have two machines, horizontal, vertical, and left and right. And he can also use these machines to detect the photon and say this is in the 0 ket or 1 ket. Okay. The crux of the QKD, this BB84 protocol, announced long ago in 1984, is Alice and Bob will choose these machines randomly. Deterministic, I mean random, but let me say they toss a coin and decide whether to send to this or it's not quantum. Decision of which machine to use is decided randomly. That is the crux of the protocol. So similarly, the Bob also will toss a coin and decide whether to use the first or second. So all the four combinations are there. Bob will use the first basis to represent the qubit, and Alice will choose the first basis to represent the qubit, and Bob will use the first machine. So all the four combinations are there. So input also, the qubits can be 0 or 1 ket, and this entire table is formed. So bit sequence is 1 1 0 0 0 etc. All combinations, and photons that are sent by this randomly. I am showing you. These are all the states that are sent for representing this, and these are the detected systems. You can observe. See, these are Bob and Alice don't know. They are using the coin tossing. They don't know whether Alice has used this or not. Bob doesn't know. Bob, how she is detecting, they don't know. What they have to do, they have to compare after detecting just the key part. I'm not saying the entire data. Key part alone, they have to detect and compare and say, if you use this, if I use this is correct. If I use this is correct. So they have to form a table. They have to work together and form the table. And once the qubit information is sent, all the qubits are sent, and according to the table, they should say, according to our table, this is the qubit that's sent. So they will. You can observe that all the information is not transmitted correctly. 50% of the information is transmitted correctly from Alice to the Bob. So that 50% is a crucial thing. If someone interprets in between Eve, someone steals the information by same algorithm. See, suppose Eve wants to interpret in between. What she has to do, she has to get 4 machines, left and right, horizontal, vertical, 2 machines for detection, 2 machines for transmission. She will do. She is not communicating with these 2 people. She's not comparing. They are not talking all 3 together. So what happens? When Alice and Bob compare their tables, they will find only 20%, 25% correct information. So that means someone has stolen the information. That's how people say this BB84 is very secure. It's a very crude algorithm. It describes perfectly how you can handle the qubits and so on, but it's not very efficient. A lot of new algorithms have come which are more efficient and so on and so forth. Just to illustrate, I have mentioned this. For a few minutes, I'll tell you about implementation issues and we'll conclude. So there is let me describe you the internet. Quantum internet means it is not between 2 points. There are many points, more than 2 points. That means, as I mentioned in the beginning, all the information is distributed across everyone, divided. Probabilities are divided. So that's an important problem. It can be very efficient. You have to devise a proper algorithm so that you say that this information is received and so on and so forth. So it's not like a broadcast. In the conventional sense, we use the broadcast. Send information to all the users. They will catch hold of the header information and see this belongs to that user, and then they will extract the information. It's not like that. All information is gone to everyone, but with a probability. Suppose 100 people are there in the audience. Everyone gets the information, but with only a probability. That means everyone is not getting. Suppose 1 by 100 probability, for example. So you have to have a mechanism to combine and then group. Okay. So I will not dwell too much about those. Now let me go a little bit of photonics implementation. So as you know, photonics is the technology of light, conventional. I'm not saying this is not a quantum slide. So a lot of applications are there now. Sensors are there. Communications is there. Optical computing also has come. So many signal processing can be done with light. So many things are there. Professionally speaking, lot of technology has progressed in photonics. Then a lot of academic activities there everywhere in universities and companies. Then a lot of national initiatives are there. In India also, photonics initiatives, there are a lot of applications. So these are all the technologies, integrated photonics for quantum technologies, mainly based on silicon. Right now we have silicon. Then in the future, people will foresee to indium phosphide, gallium arsenide, etc. I want to show you a few devices to complete. So a lot of nonlinear effects are used in crystals like lithium and KTP. So the conclusion of this slide is we need to go for active materials. Silicon is not sufficient. So a lot of devices are there. I'll show you a few. Just this is an example I'm showing you of photonic devices that may be useful for quantum information. So this is on the chip, integrated photonics. So you have gratings for the input-output coupling. In some other lectures, you must have heard about photonic ICs, okay, in this conference itself. So you have a ring resonator which can tune into some particular frequencies. And then this is a grating which can act as a filter or a reflector. And you have you can couple two ring resonators and so on. So you have to work out all these things. See, I have just mentioned these are the devices, coupler, etc., etc. But what are the quantum properties is what we have to study. If a single photon is launched through this coupler, the input, as it passes through this ring resonator, this reflector, this output rings, etc., what is happening to the qubit state, what is the probability of outcome, etc., is what we have to understand and to use these things. So for more details, you can see some of these papers that are available. So similarly, generation of quantum information and qubits, modulation, that if you have a conventional light wave carrier, how to input. You see, just I would like to bring to your notice 2000 kilometers quantum communication link they have done, Chinese. They are not transmitting a single photon. At quantum state, they are transmitting. That single photon is embedded inside a big light wave of so many kilowatts. Suppose you take 1 kilowatt of laser beam, transmit to satellite. It has got n number of photons, 10 power, very large number, not a single photon. But the quantum property of single photon is embedded or modulated into this 1 kilowatt energy. And at the satellite or the other end, they have to extract the quantum information from that. That mechanism is needed. If you want to set up a quantum communication link in your lab, in your university, if you want to set up a small link from this end to that end, you have to understand that part first. When we describe principles, when we describe in the class, when we put all these mathematics, we are talking about only one photon. But in practice, you have to see how this will be embedded inside the classical system. It is also possible to have a fully quantum method of dealing, because as I said in the beginning, it is not only atomic systems, the physical systems, the strength of this object, for example, is a quantum property. So somehow we should have a mechanism to use that. Right now we don't have all those mechanisms, but I suppose it is happening in the real world systems, in the atomic, in the biological systems and so on. The real quantum communication or quantum information processing is happening. For example, in our eye, when we detect light, it's a quantum phenomenon, not the classical phenomenon. Only the lens part, the focusing, etc., is classical. But how the brain is detecting, how the cells are detecting these photons, they're all quantum phenomena. We have to understand why it's happening. Okay, let us move on to one final slide. So there are a lot of information there, papers are there for those who are interested. I will little bit about our lab. I will mention what we are doing. So we have done quantum cryptography. We have 3 PhDs in this subject. So one of them have done quantum algorithms using the photonics and so on, random number generation and all those things we have done. I'll show you one slide just to give the information for those for the audience and the people who are interested. See, this is a Y branch on the integrated optic chip. You can make it on silicon or glass or lithium. This is a top view. You can launch light into this and then observe at the output ports. Conventionally, the power will be divided across 2 output ports. If you are launching a single photon, the output is a linear combination of these 2 states, 0 state and 1 state, 0 minus state, 0 minus 1 state. Then in our lab, instead of using the energy levels of the photon, we are representing the qubits by the modes of this, like photon. TE mode and TM mode can represent two different polarizations of two different modes, or TE0 and TE1 mode also can be used. So if I represent the qubit state by TE0 and TE1, then what happens is what we work out, all the mathematics of that, solve the wave equation and correspond to the Schrodinger equation, and you can say this is the outcome. So we can take the parallel from the beam splitter. The conventional, you have the beam splitter. There, of course, you don't have the modes, you have only the horizontal or vertical polarization. So in integrated optics, you have the advantage of using modes for all these operations. So very interesting thing. A lot of things can be done which cannot be possible with conventional thing. Now sometimes they are not possible with quantum bulk also. A lot of phenomena are available. So this is an example of a Hadamard gate, what I mentioned in the beginning. That's all to give you. This is an implementation using photonic crystal structures. You can fabricate these Y branches and all these ring resonators, all these devices. This is one of our earliest paper, first paper we did on the photonic crystal based Hadamard gate. So BB84 protocol that we talked about just now can also be implemented, and this is how it looks like in the block diagrammatic form. So this is about the single photon sources generation, etc. That's how I think I have to present. So thank you very much for listening. If you have some questions, we can take. And a lot of activity going on in India. People who are interested, may please look at those, and a lot of applications. Okay, thank you. Let us conclude because I have crossed the questions. Biosensing. Okay. First of all, not related to quantum. Biosensors means you have to identify certain elements like enzymes or blood sugar level, cancer cells or something. Some biological object you want to detect. Biosensor means. How do you do usually? Typically, you have to create some, normally, conventionally, whatever the people are doing now, there is an electronic device. You have an electrode. The cell will react to that electrode. It will excite some parameter, current or something in that electrode. If a particular cell is there, you have a certain amount of current. Or capacitive device. The capacitance will change. The resistance between two electrodes will change. That's how you are doing the sensing, biosensing. Can we see this? Biosensing implies you are trying to detect some biological objects. There is other important sensing also many people do. This is biomedical sensing, physical. That's also biosensing. Physical parameters like the pressure, temperature of a human body, biomedical. These are also necessary, but you have to separate out them from the what we are talking about. We are talking about biological sensing, cells. Now, optical method is going to be very, very sensitive. This is what people have found. That means you excite the cell with a light wave. You excite the cell with a light wave and see how it reacts. What happens? Suppose the spectrum can change, wavelength can shift, direction can change, and so you can detect that a particular cell is there. Most of the time, you have to create an analyte. You have to mix this blood or biological objects through some liquid, ethylene dioxide or whatever, I don't know. Analyte is called. The analyte properties are influenced by this cell. For example, refractiveness can change. If the cancer cell concentration is so much, this analyte properties, refractive index. So based on that, based on that refractive index sensing, you can do this biosensing. That is conventional biosensing. The biomedical, the objects, the cells will be influenced by light. Next, the light is very small, only a few photons are launched. Or we want to study how the cell reacts with one photon. Suppose one single photon is incident on the cell. What happens? It's an important question. The cell will react to that photon and changes to something. So this can be called as quantum sensing. In fact, that is what is happening inside the body. We are seeing the bulk objects. Bulk effects is what we are seeing when we observe, say, some spectrum. Suppose you observe, you say, take a sample, launch light onto that, and observe a spectrum. Spectrum change. That is a bulk effect. But what is happening internally is quantum effects. The cell is absorbing only one photon or two photons. So the quantum sensing is happening there. So correlating with what we studied today, we have to understand the mechanism between the quantum phenomena and the bulk phenomena. When you see, for example, single photon absorption. If one photon is absorbed, how the cell is reacting. If two photons are absorbed, how the cell is reacting. And how it is reflected in the bulk output is what we should know. By observing the bulk output, we can say this particular quantum phenomena has happened in such cell. You can do such quantum sensing. That's a quantum level of application of all these things. And all these things we should study the mathematics of that. We have to examine what is the spectrum, what is the principles, all those things, step by step, point by point only. We cannot simply suddenly say we want to invent some quantum biosensor or something like that. Fully complete cancer we cannot detect. Okay? Some specific property we have to target, and it can be addressed, and we have to work out fully in principles. Then of course, definitely experimentation is needed. We have to create some devices which will operate with these things. We should be able to detect something, currents or voltages or light levels we detect finally. That can be called as quantum sensing. So it's a hot subject. A lot of people are working on this. Yes, including, see, just now we talked about cells. There are a lot of other biological objects like viruses. They have their own mechanism of dividing, spreading, sometimes very rapid. So there can be a drastic change in the output. Based on such things, based on some observations, we can say certain virus is there or not. This is a very broad genetic statement, but it is possible to detect. A lot of cells, like cancer cells, will multiply like anything. So within a short time, you can say that so much output change is there. So something is there. And one of the things that many people want to do is to detect early. When very, very little amount of biological material is there, we should be able to detect. We can say that this is there. Then you can take some measure. If it has gone too much, then I think very difficult to. And also, people are related to this. People want to understand how human beings and biological objects are behaving with respect to certain light and these phenomena. So you can say that most of the phenomena are quantum in nature. We should not say this is classical, this is quantum, etc. This is a phenomenon which will use the quantum principles that have been invented long ago. So when we do a lot of things, when we understand things, when we blink or when we see something, etc., quantum phenomena is happening. This table is very strong because of the quantum properties of the atoms, not classical properties. But this is bulk. The strength is a bulk property, dependent on quantum properties of the. Later on we can debate. Can be touched. Those who are interested in all these subjects can look at magazines from the IEEE Photonics Society. If you are interested in biomedical, EMBS is the chapter that is needed. All those things I suppose you know. We'll debate later on. Okay, thank you.
So the presentation is on extrapolation of possible foot ulceration based on gait and foot type. So thank you for this opportunity, first of all. And I'm Bhargavi Haripriya from Department of Biomedical Engineering, SRM IST Katangulathur. So let's quickly look at what exactly is this foot ulcer. We can say foot ulcer is an open sore on the foot, and it can be a shallow red crater or it can be a deep ulcer. It depends on the scenario and the kind of length or the kind of scenario situation in which the ulcer has occurred. As per the WHO statistics, 1 in 20 people with diabetes have a possibility of developing foot ulcer. And the common causes include neuropathy, cellulite, trauma, poor circulation, peripheral artery diseases. And it also is possible they have unusually formed toes. That can be a reason for foot ulcers. Then the reasons that we are concentrating are the last three, which is the unusual pattern of the walk, okay, where the kind of pressure the person puts on the foot might vary and it may lead to foot ulceration. Or while the person is walking, there can be a friction in the foot and toe rubbings, and that might lead to foot ulceration. Then there is obesity is definitely a factor that is involved. So if you're looking at the pattern that we are concentrating on, includes gate analysis and ground reaction forces. So gate analysis is nothing but the study of locomotion, and you can say it's basically like so gate analysis is the study of locomotion, and it deals with how exactly you're walking. It includes stance phase and swing phase, and like a complete gait cycle is involved there. Then ground reaction force, or GRF, is your gait parameter, which can validate the state of disorder of the patient's movement. Normally, ground reaction forces are calculated based on the body weight and the acceleration of the person while they are walking. So there is another factor which is called as the foot type. We have considered three main categories of foot types, which is neutral, flat, and high arched foot types. The foot type significance was also tried to this work, that is what we had tried, like to look at like the significance of ground reaction force along with the foot type. And the idea of creating this work was to make it as user friendly as possible. So all the data was collected using a smartphone, where the mobile app is with the inbuilt sensors of the phone, and the mobile app in itself can be used as the transmission part, which can be further used for data analysis. So right now, this particular application was created for Android smartphone using MIT App Developer. Our work basically constitutes of 4 main stages, like of course there is a welcome screen and about screen. Then there are these four screens which are the main data capturing screens. So we have acceleration, body mass index was calculated, speed, and then ground reaction forces were calculated, for which each one of those are given in different scenarios. So here's a screenshot which shows how the application would basically look like. I've used only 3 screenshots here, which shows the main screen. Then the acceleration was basically calculated both in numerical and also as a graphical way, which is the second part. And the third thing is for calculating the ground reaction forces based on the body mass index, acceleration. And then, like, the final possible inference was also displayed here on the screen. So here's a picture which shows the acceleration, which has been taken based on the accelerometer inbuilt in the Android phone. So you can see 3 different colors here, so which include the x-axis, y-axis, and z-axis. Sometimes in case the person is like having shaking, we try to inculcate like that also, as in case there is a nerve disorder, we wanted to include that also as one of the parameters. So we have given that shaking as one of the parameters to be considered. So here's a screen where the weight and height parameters have to be entered by the user, and then the user will be able to see the outputs here. So this is basically the data collection pathway. We had selected a even ground, but instead of having it as a cement ground, we had considered a paved pathway, and the distance of the pathway was fixed to be 10 meters. So in this particular pathway, the smartphone was placed on the subject. As you can see, it was placed 6 inches above the knee point. So we have used 6 inches above the knee point as a common parameter to have uniformity in data collection. So once we have done that, we have used this sports wristbands, in which the mobiles were placed, and it was placed on the thigh of the person. So if you look at the methodology of the overall working, so we have the mobile application initially has to be switched on. Then the weight and height data was obtained. Then the mobile was placed on the thigh of the subject. Subject would be asked to walk this distance of 10 meters. Speed, acceleration, ground reaction forces was obtained. And then we have also asked the person to step into water and then without the footwear, of course, and place his foot on a brown plain street paper. So based on this, the foot type was confirmed and it was done visibly. For this particular thing, we conducted the readings from volunteers, and all of them basically belong to a age group of 30 to 50. It was conducted for male population alone. And we had 3 categories of males, like one was below 30, 31 to 50 and above 50 years. Then based on the foot types, we had categorized the population into 3 types: normal, flat foot, and high arc. And based on BMI, we had classified the people into 3 types: normal weight, overweight, and obese. We didn't have any people in the obese category, only the overweight category were there. And the total data collected was around 19 people. So what we were able to analyze based on these data collection was, based on the 3 types of foot types, normal, flat, and high arc, we could observe that the ground reaction forces in normal foot for people with normal BMI was around 1.7, which is like, a pretty nominal value, which is your Y direction acceleration that we have considered. So why we consider only Y direction is because the person is moving in a singular direction, singular angle basically. And we have also observed that the people, as the weight increases, even for normal foot, the ground reaction forces are considerably increasing. So you can notice that people with flat foot have higher ground reaction force. Now, how does this affect our possible foot ulceration is, as your ground reaction forces is increasing, that shows that the possibility of getting the foot ulcer is going to be more. That is what the literature says. And we will not be able to modify the foot types at least, but we can definitely work on the ground reaction forces. So the way you walk can be modified so that the person will be able to ensure that the possibility of ulceration is going to reduce. And what we have noticed is, once we have mentioned the fault in the foot type of the person was able to adjust their walking pattern, and it helped those people to improve their improve their walking patterns. And another factor is, we can definitely advise them based on their body mass index, whether their ground reaction forces are more or less. So in conclusion, we can say that as the body mass index is higher, the chances of foot ulcer development is also going to increase. And there is a close relation which is established between foot type and shear stress distribution. By shear stress distribution, I mean the ground reaction forces here. And right now, the application is totally offline. Even though it's user friendly, at a given point of time, we are able to collect only one person's data. And this particular application was developed exclusively for Android smartphones, and it's not compatible with other smartphones which are like based on the Windows applications or Windows OS. So this is one thing which we are planning to work on. And we hope to make it into a full-time gait analysis tool, so that like there are other sensors which are there within your smartphone. We are looking into working on those sensors and trying to improve this, and also make it as an online application so that the recordings can be taken up as a permanent information, or we can have a clear-cut database, place it in a cloud. So that is what is the future plan. And with this, I think these are a couple of our references that we have used. So with that, I think I can conclude this presentation. Thank you. Any questions?
Questions, please.
how sensitive is your measurement?
Sir, could you repeat the question?
How sensitive is your measurement?
He's asking how sensitive is your
How
measurement?
sensitive? Sir, right now what we have seen is we have checked once with an individual accelerometer, but we were not, and like whatever we were getting in the accelerometer as an individual accelerometer with a, we had tried it with Arduino Nano board, we had inculcated one. And the readings what we are getting in our mobile phone and the accelerometer in the Arduino Nano board were like almost similar. So with that, I can say the value obtained in the accelerometer in the mobile phone and an individual accelerometer are similar. In terms of sensitivity, we don't have an exact answer for that, but like I can say that like maybe it's around 85 to 90%.
Okay. Any other question? Okay, so I have one small question. You have collected data for 19 samples, right?
Yes, sir.
So do you think that concluding some statistics from 19 samples is enough?
No, sir.
What's your take on this?
Yeah, we were actually targeting for at least 100 samples, but we didn't have enough time. So we had initially collected only 19 samples. So we're just presenting it as an initial extrapolation work where we wanted to justify that there is a possibility of ensuring that your food type and the body mass index will play a significant role in food ulceration. But I do agree that we need to work on more samples, and we are also planning to work on male and female population criteria. So, but like probably in the next semester we'll be working on that.
Okay. And there is one more question that if you go to orthopedic for this gait kind of problems,
yes,
and
sir.
if the person is maybe flat-footed or has a wrong shape of the foot,
Yes, sir.
so they recommend some different kind of shoes or footwears which have some arcs inbuilt on them, so that the foot shapes get recovered and the walking style can be improved. So can you design such kind of things with your method? That if you say that if the arc is something like this, maybe you will have less force, the walking force as you're calculating. Is something like this available on your method?
Right now, this is a offloading of foot is a parallel work which we are targeting for.
Okay.
That's the reason like we had tried to check on ground reaction forces as one main application, sir. I mean like that's a different project which we are looking for. We have something else going on where we are planning on offloading of foot, where probably we can have medicine implants through the offloading method itself. We are working on that, but probably that's for the next.
Yeah, there are good foot implants available readily where the specialists are available. So you may please consult them if possible.
That possibility is highly there, sir. But normally a food type, what we are talking about, technically should not affect your day-to-day living. But how we are trying to concentrate is based on your food type and increasing your obesity, the possibility of ulceration would increase. That is what is our final conclusion towards the work.
Okay.
Even if you're having a normal food type, but your obesity is increasing, the possibility of ulceration is going to increase. That is our first conclusion. Second conclusion is if you're having an slightly abnormal food type, the possibility of you getting a food ulcer will be much more than a normal food type. So these are the 2 points we are trying to put forth.
Okay, fine. So thank you for your presentation. So we'll move on to the next presentation now.
I will be presenting the next presentation also.
Okay, fine. So please go ahead with the next presentation. The title is Tracking Various Lower Extremity Parameters of an Athlete During Squats Using a Variable Performance Analysis System. So you may start the next presentation, please.
Just a second, sir. I hope my screen is visible, sir.
Yes, it is.
Okay, thank you. So this again is involved with lower extremities only. So what we are actually looking at, the topic of this presentation is tracking various lower extremity parameters of an athlete during squats, and we are targeting for a wearable performance analysis system. Again, thank you for this opportunity. This is one of our student work which I would be presenting, and here's a list of authors that are involved in this particular paper. So technology, that of having wearable technology is in terms of competitive sports, and an athlete analysis or athlete performance analysis is very crucial in terms of performance and training. And we can use these wearable devices so that the trainer is able to analyze how the athlete is performing. According to NCBI, the training error, whichever is there, around 60 to 70% is what exactly will result in the injuries like for the athletes. So we have also observed that annually about 4.5 million people will have to be treated for sports injuries. So what we are proposing is for a system which can incorporate multiple sensors in a single setup and try to obtain the performance analysis. So this is a wearable device which is a preliminary screening instrument for analyzing of lower extremity parameters, and we are concentrating on athletes here. So let me take you through the simple block diagram. We are using two different Arduino microprocessors processors here. So one is for collecting the data of your accelerometer. The other one is for collecting the data of the foot pressure sensors. And there's also muscle sensors which are used, which basically is your EMG sensors, which can be used for collecting data of your muscular activities. So here's a picture which shows the two different wearable parameters that are developed here. So this is an EMG module, what you are able to see here with this yellow red leads, and this one out here, the yellow one also, a green. So, and we have used 6 sensors for obtaining the foot pressure. There's an accelerometer, and we have used 2 9-volt batteries. 2 9-volt batteries are needed because the number of sensors are more, and your EMG sensor in itself needs an individual battery supply for it. So we have a Bluetooth module incorporated here, which can be used for transmission of data. Okay, so let me take you through a quick video demo. So the person is like wearing, we have placed the thing in the shoes or the slippers. So the person can switch on the accelerometer. So once it's switched on, you are able to obtain the data in the mobile phone. Then we're asking the athlete to perform the squats. So you can see all the 6 foot pressure values, the EMG values, and the different axis values are obtained. And we are obtaining it for both the left and right foot. So here's a comparison table which shows like what would be the ranges of values that are varying. So the 6 pressure sensors which are placed in such a way. We have used multiple literatures to identify what would be the best areas where the pressure values can change, which were considered to be your forefoot. 2 sensors were placed in the forefoot, 1 was placed in the heel, and there are 3 points in the midfoot. There are 3 points in these 2 are your forefoot sensors, and these 3 are the midfoot sensors, and here is your heel sensor. So what we have observed is these are the main areas where your sensors, where the person will put more pressure while they're performing the various activities we're talking about. And what we have noticed is the pressure is maximum in the forefoot and in the heel region, then comparative to your mid region. And the x-axis movement and y-axis and z-axis, all the three axis movements while standing and squatting do vary. And the muscular activities are more during the squatting while comparative to your standing position. And here's a pictorial representation. What we have done is we have made the person do 5 different instances of the same standing and squatting performances, so that like we could take an average of the values. And here's a picture which shows the different types of the 6 different sensors. I'm sorry, the 6 different sensors here. So we have like what we can observe from all these values is for multiple instances, the values are similar, but the pressure in the heel and forefoot slightly increase as the person is doing, as the number of instances of doing the activity is increasing. We are not telling that it's like randomly increasing, but it is slightly increasing. There is another factor that we have tried to check out here, which is checking whether there is a symmetry between the person's activity. So this was the second factor that we were observing. Normally, when an athlete will have an injury or a problem in one foot, they tend to do an activity, or they favor one foot more than the other foot. So this particular parameter analysis also helps you to identify whether there is any such extra favoring which might lead to problems while the person is performing in the regular parameters. Okay, so here's another picture which shows like the right, here's one which compares the right and left foot values while standing and squatting. So you can see this light green color and yellow color are the values for standing values, while this green is left and yellow is right. So for this particular instance, you can see that initially the person was applying more pressure in the right foot while standing, but you can notice during squatting it has evened out. The reason for taking multiple instances is this: you can notice that after the 5th instance, the values are almost similar for left and right foot. So by making the person do multiple squats and multiple standing activities, we were able to average out and do any eliminate the errors that were possible because of this. So here's a graphical representation which shows the left and right foot comparisons for accelerometer. What we have noticed is because the person is moving in vertical direction only, so you can notice the value variation in y-axis, and that is where the maximum value is there. And electromyogram values, as I have already mentioned, it's more while squatting when comparative to the standing. So this also helps us to identify whether the person is going to be using the appropriate muscular force while doing the activity. So by comparing the independent parameters of athlete for a single instance, what we can conclude is the range in which the parameter values are going to change for this particular athletic person. And by once we have enough data, we can like compare with multiple athletic people, so that like we can see whether they are falling in the same category or not. And by comparing for 5 different instances, we were able to conclude the foot pressure at forefoot and heel is greater than comparative to your midfoot. And the pressure is greater at heels, which is exactly what we have found in the literature also. And as I said, the parameters for both legs are almost similar with very slight variation when the person is standing. So this basically proves our theorem of symmetry. So when you're doing an activity and if you're a normal person, then you will have a symmetry in both the foot. But if there is a problem in your activity or you had an injury, then there is going to be an asymmetry in your parameter correction. So our this idea basically came to us during COVID period, where we knew that sports people were not able to get out much and not able to do their regular practices and performance analysis and all. So we wanted to create a very low cost wearable user friendly device. And again, like mobile application was inculcated so that the person will be able to transmit data in a much easier and comfortable manner. So right now, this value assumption is only for two activities, standing and squatting. We are working on trying to develop it for multiple applications so that like we can give this device for specific workouts. So individual basically what we have tried to do in this. Here are a couple of references that we have mainly concentrated on. So that brings me to the conclusion of this presentation. Thank you for listening. Any questions?
Yeah, thank you for the presentation. Any questions? So I have a couple of questions.
Yes.
Apart from athletes, what are the other people who can use this? Can, let's say, for example, classical dancers in Bharatanatyam form or in any other form, can they be analyzed with this method?
We can, sir. Actually, our idea was, apart from athletes, we were planning on rehabilitation, planning to give it for people undergoing rehabilitation after a surgery or so, knee surgery or so. That is what is our target actually. So athletes basically were considered so that we can get the normal parameters. And once we have a good database onto the normal parameters or the normal range of muscular activities, right now we have done it for a specific age group, 18 to 25 years alone. But we also have to expand this database. We want to make it to 18 to 60 or like maybe 15 to 60. And then we can compare it to all the people who have had a surgery and whether they are recovering properly or not. That is the idea behind like this symmetry calculation. If you have any surgery in your right foot and right knee, and you're basically like recovering, you have done physiotherapy, and after that, like what we'll do is we'll make you do this activity, standard squat, do it for 5 times, and it can tell you your muscular activities and your foot pressure, so that we'll know whether your right foot is exactly coming as your left foot. We are comparing with yourself first, then we'll compare it with a database which we already have for your age group. So this is what is the penultimate plan that we have. We do have a physiotherapy unit where we are working for this.
Okay, that's good. So the second part of the question is, when you are talking about squats, more than like apart from the foot, there are knees, quadruples, hamstrings are involved, which will be under more stress than the foot itself. Then have you analyzed those things, or is it still under process?
It's still under process, sir, but actually we had concentrated on foot pressure. It all amalgamates to the foot pressure, sir. So if your hamstrings and quadruples are not working properly, then you will not be able to place proper pressure on your foot. So this is what is our basic conclusion that we have come to based on like a lot of references that we have had. Whether you are doing like different biomechanical parameters or your normal gait, your muscular activity eventually affects your foot pressure. So that's the reason we took this as an easily measurable parameter. So if we are able to measure the foot pressure, I think we can definitely take it up. And I mean, like this can be, as I said, this is a user-friendly and low-cost device. So this whole device basically costed us around 1,500 to 2,000 rupees alone, including the accelerometers and all the sensors that we are talking about.
Okay.
So our idea was to give it to the individuals so that they can do a regular day-to-day analysis, and we can see whether they are progressing regularly or not.
Okay. So we'll conclude now. Thank you for your presentation and time.
Thank you so much.